Please allow me to introduce Professor Dr. Harouk Sujour, who will be talking today about the blast effect on airport structures. This is the first keynote speaker in this
في هذا المؤتمر السابع الأردني الدولي للهندسة المدنية، والذي تنظمه نقابة المهندسين الأردنيين. الدكتور حلوق سجولو هو عضو من جامعة الشرق الأوسط التقنية قسم الهندسة المدنية. إنها عريقة في تركيا، واحدة ربما من أوائل الجامعات في تركيا، والتي تدرس باللغة التي درست باللغة الإنجليزية لفترة طويلة. البروفيسور سجولو هو مدير مختبرات الهندسة الإنشائية والزلازل. هو بروفيسور في قسم الهندسة المدنية في أنقرة في تركيا، وهو أيضا يدرس أيضا في برنامج الدراسات العليا في بافيا في جامعة بافيا في إيطاليا لهندسة الإنشاءات والزلازل. هو الآن مدير الهندسة الإنشائية، مختبرات الهندسة الإنشائية والزلازل في جامعة الشرق الأوسط التقنية. إجراءات
which was an initiative for a campaign. It was called "Should Not Be Knocked Down" campaign in Istanbul. So they did the assessment for 150 buildings in there and how to retrofit and develop these buildings. So it was within the scope of the Istanbul Earthquake Master Plan. He was the technical coordinator of the school retrofitting program of the Ministry of Education during 2005 and 2007. He is serving as the coordination committee member of Turkish Seismic Code since 2004. Dr. Sujoğlu is the national delegate of Turkey at the International Association of Earthquake Engineering and president of the Earthquake Engineering Association of Turkey. He is the editorial board member of Earthquake Spectrum, Journal of Earthquake Engineering, and Earthquakes and Structural Journals as well. He is the recipient of the 2012 Science Award of Partner Science and Education Foundation. He is the author of several papers published in international peer-reviewed journals, and also recently he published a book called with the title Basic Earthquake Engineering, which will recently published by Springer. The lecture will be 1 hour. Dr. Sujoğlu will make his presentation, let's say about 40 minutes, and then we'll open the floor for discussion for about 20 minutes. So please allow me to introduce Dr. Sujoğlu. It is our honor to have you here this year as well.
Thank you, Mr. Chairman. Dear colleagues, Assalamu alaikum. It's an honor for me to be here as a guest of the Association of Civil Engineering of Jordan, and I always feel in a friendly environment when I come, so I'm quite relieved among you. As Professor Moaz announced, actually my research field is earthquake engineering, and earthquakes are caused by natural disasters. But there are other disasters which may be more disastrous than natural hazards. These are man-made disasters. And terrorism is one of them, which arises during times of war and unrest, which we are going through since a couple of years in this area. We engineers and architects are naive people. We think that the structures that we design will serve and survive in a friendly, peaceful environment. But in case of such evil human acts as terrorism, actually they are also subjected to more severe effects that we don't usually consider in planning them, in designing them, in constructing them. This happens by time, then we may just perceive that maybe there are different effects that we may consider on our structures in case of such disasters may occur. So today I'll just talk on safety of airport structures against blast attack. Why did I take up this topic? This is not a research topic actually, it's a research topic in itself, but I'm doing some engineering applications in certain airports, both within Turkey and outside Turkey, and I consider that they have many similar features. They look like each other, and they have similar weaknesses, they have similar risks. So how can we consider their risks, how can we reduce their risks in case of such unexpected events may occur. So airport terminals are one of those buildings which are vulnerable. Why they are vulnerable to terrorism more than the other structures? Because there's an increased public use of major international airports. We are using airport traffic more and more, and we need more larger international airport terminals. And when an attack occurs on an airport terminal, it attracts wide publicity because it's an important building. We had examples of this in recent years in Brussels and in Istanbul. And since there are passengers from many nations in an airport, so that makes a much wider publicity. That's what terrorists are actually looking for, much higher impact on the public. So airports are more vulnerable to such attacks compared to other buildings. For example, hydraulic dams may be also vulnerable, or nuclear power plants, but they are more remote and not accessible to people. But airports, everybody goes in and out, so it's easily accessible. So airports have such a vulnerability. That vulnerability also arises from their structural forms. They are exposed structures, I'll show. So they are sort of naked structures. When you see from outside, you can just see how the structural system is configured in an airport structure. And if you're looking for a critical location with an evil eye, you can find them very easily. So several critical locations are also easy to reach by vehicles because they are not considered to be attacked by a truck bomb, for example. So that's why we are naive. We should maybe think of that in the planning phase. And even if a terrorist is supported by an evil engineer, a good guidance can be taken where to replace the bomb and blast the structure. So this is a typical rendering of a modern airport. You can see what I mean, actually. So all main structure is exposed. It can be seen from outside. You can see that, well, usually they have a very elegant roof structure, and the main structure is underneath the roof structure. The departure level and the arrival level and the luggage handling structures are under the roof structure. And this roof structure is supported by again, some slender columns, which are also carrying the internal structure as well. And so it is just very obvious how this structural system works and what are its vulnerabilities. Also, there is lots of traffic. There is people every day, and vehicles can go through this structure, and sometimes they can go underneath. Usually, modern airports, traffic goes underneath the structure, which is a high risk actually in such cases, but it's not considered. Surprisingly, it's not considered. For example, yeah, okay. So what are the types of attack that can be expected? Now we are talking about the worst case scenarios. We are not talking about good people. We are thinking of bad people. So we know that certain attacks in the past have been realized by gun attack by one or several individuals, or a bomb carried in a backpack, for example, by an individual, or explosives carried by a truck vehicle. So the intensity is increasing. Now, normally we think that it shouldn't happen because there's lots of security clearances they cannot pass. But it happens. Why it happens? Because individual attackers can be stopped at safety checkpoints, and a truck can be stopped at the vehicle checkpoint. But there are always weaknesses in safety checks. And, inside assistance is always possible. We cannot guarantee everybody working in a terminal building that they are safe and they have goodwill. So hundreds of people are working, and terrorists always can find internal assistance. And if security is increased, then there's a counterpart of trade-off of increased security with delays to access the airport. We are all suffering from that. When we go to the airport, we go through several security checks just because of the other people who can attack us. So we suffer actually. And as the security increases, then entrance to the airport can be very difficult, can be very painful. After the attack in Istanbul, there was huge security checks to enter the airport. So many people miss their planes, and this is not sustainable. So we have to find a midway, and maybe in the planning phase of such vulnerable structures to terrorist attacks, we should just reduce the risk, which is not easy, but this is a new problem. And a car bomb may cause collapse of the entire terminal building, which is the ultimate aim of a terrorist. This is possible. We have to at least reduce this risk to zero, and then reduce the other risks by better security checks. So today, I'd like to just do an analysis for a typical building. I don't know how you can see, but it's not a very good picture. But again, this is a plan view of a typical airport structure with a roof structure on top. Do we have a pointer? I didn't take it, but maybe we can find some. There's a roof structure, then there is a departure level structure, then there's an arrival level structure. And if we do a close-up view, if we just make a close-up, you can see that here there's a parking garage, and vehicles can go through the building at this intersection. The columns which are rising up to the roof are very slender and tall. So you can see that it's an elegant structure, but also it has its vulnerabilities. Now, when we take a close-up view, this hatched region, actually it's a highway. It's a highway, 3 lanes, going through underneath the structure for pickup, for passenger delivery, and I cannot see even from my screen, but you can see that this column, the first column before the overhang region, is just going. It's on the way. It's on the access way to the airport. So any truck loaded with explosives can park here. Maybe I can show. It's very bright. column is getting damaged. And in the structure, when people can park over here and explode its bomb and probably collapse the entire structure, because that overhang in that case becomes something like 70 meters. So if you have such a plan, structural plan, I need a pointer actually. There's a pointer. I can talk from here. It's no we have to prepare a scenario for any structure because we don't know the hazard. So it can be attacked at any point. We should just plan for the worst scenario case and study the effects step by step. How does it go? How does it accumulate? Well, in this case, the attack comes by a truck loaded with explosives approach a critical column. So then column carrying a large part of the structure collapses. So this is a primary effect. Also, the slab and side partitions, if any, covering the explosive space fragments. This is a type of secondary effect because each fragment becomes a bullet. Bullet spreads around and hits anybody in the field. So this is a sort of secondary effect. Of course, the slab will probably collapse. And the structure of the collapsed column perhaps may lose its stability, leading to partial collapse of the this geliyor mu siz? No, it's not. No, I think no. Still no sound. There is? Okay. Well, then at the third stage, the structure of the collapsed column loses stability and leading to partial collapse of the terminal structure. I should use it. Maybe I can use it. So now our task is to go through this worst case scenario and investigate step by step what happens and what are the consequences. So this partial collapse is of course a primary sort of damage, and there are also consequent damages like downtime of the terminal structure for a long time. It's a huge investment and it's a huge loss of money, in addition to some human losses or injuries. So this is not bearable actually. It's not acceptable for any such type of structure. So in this presentation, I'll investigate how primary effects can be handled, how can we measure them, how can we analyze them. So this we start with a blast effect on column, which is real engineering now. Now the column that is carrying a roof structure of an airport is usually very large. This column is typical. It has a diameter of 2 meters and a height of 10 meters. So what happens here is that we have to make a scenario. We assume that the blast, the explosive can be detonated at an elevation of 1 meter and at a distance of 1 meter from the column, because it's just in the middle of the traffic. It's just dividing lanes. So very easily a truck, once it passes the security, can go to that column and blast off. So technically, blast is a pressure, an air wave which is reflected from a rigid surface on its way. So it has to be calculated accurately in order to analyze how the column will be affected from blast or any surface, any structural surface. Technically, blast can be simulated with a triangular loading. Oh, thank you very much. Thank you very much. Blast can be simulated by a triangular loading, pressure versus time. This pressure PR is the reflected pressure because it hits the surface and then it's reflected. And duration starts at T0 and TD is the duration. These are very short durations in milliseconds, thousandths of a second. And this pressure is a function of the weight of the charge, how much exposure is determined, the distance from the surface, and the angle of incidence. When this angle is zero, you cannot see it very well, but when the angle is zero, it's a direct reflection, so it has the highest influence. As the theta increases, then the effect gets less. So in this geometry, the blast affects this chord length. Pressure is applied to this chord of the column, but in decreasing values from this theta is equal to 0, theta is equal to 60 degrees. So we have to calculate this. And it has a variation along the height of the column. So at each point, we have to calculate pressure versus time curves, such curves, after discretizing the surface into certain small elements. And this function should be calculated for all of them separately and then applied in a time story analysis to the structure. It's very short, but then you can calculate what happens inside this column. So again, this is our function, and we calculate this pressure for an explosive charge of 2,000 newtons. So this is 400 metric kilogram, which can be carried easily by a truck. And so since the calculating of this distance r is equal to 1 meter, and theta 0 degree for the reflected ray, but it changes from 0 to 60 degrees in both directions. And also there's a vertical propagation of wave, which affects R as well. So R has two dimensions. Now, under this explosive and that function, PR0 or theta 0 degrees, so close distance to the blast, at each point, the pressure of 240 megapascal develops. This is much larger than even the compressive strength of concrete. And T0 arrival time is very short, and duration is less than 1,000 per second. And so this should be applied to the column, fixed its basis perhaps, and we can do only linear elastic analysis here on the surface of the column to calculate how shears and moments are distributed inside the column, and whether the capacity is sufficient to resist it. So this is our model with many 3D elements, and so we start from here at light, so the blast wave goes over the column height, very short, and then reflected and comes back. So maybe I can show a simulation of this pressure, how it goes. So this is a very slow motion, just gives you a feeling of how the pressure wave is propagating up into the surface. The pressure intensity is very high, but normally it's roughly, so you can maybe follow from here, it goes up, and then it will disappear. Okay, well, this is the envelope of maximum displacement, which is calculated. But this is the envelope, so they are not synchronized, they don't occur at the same time. When, for example, displacement at 1 meter level is at this level, probably the curvature, the displacement is usually something like this. I should have drawn it as well. So curvatures are very high. And now that moment is the second derivative of displacement, curvature, and shear is the third derivative. So as this curvature goes up, then enormous internal forces develop. So this is it's an envelope. They don't occur at the same time. But at the given instant of time, this displacement is something like this. So it corresponds to very high curvatures and shears. And these are the calculated envelopes of shear and moment. These are the shear envelope, which goes maximum here, those detonations around here, and it's the moment envelope. And we calculated the capacities, and these capacities are actually quite large because this airport is in a high seismic region. There's already so much reinforcement. We're using the existing material strengths, meaning that we don't use the characteristics, we're using real actual stresses, so these are increased both because of the higher strength and also the dynamic effect on the material. So looking at shear, I know there are some small blue lines which are showing the capacities at the support regions. So these are much lower compared to shear forces acting on the system, and moments are closer, so that here there will be plastic hinges at the moments, of course, but this system directly fades in shear. It just shears off. There's no way to save this column under such a program of exposure. So what we considered in the beginning was whether we can increase its shear strength by covering it with a steel at least 2 centimeters of steel coverage was needed, and there are more than 50 such columns that can be reached by me. So this was really expensive and very delaying the construction, and so we considered different types of precautions whether we can reduce the risk. So one thing is don't let the traffic along heat, but it was already there. So there is no way to change, and they're still thinking of that. So the first stage is down, so the column fails. So let's see what if column fails. If the column fails, what happens to the other parts? We should go one step further and then see whether there is a collapse, there is a partial collapse, or what are the consequences. And so this is the first structure that we should consider is the roof structure, whether the roof structure stays or not. This is the plan view of the roof structure. Maybe I should also show here that, this is where the explosion occurs. This is the worst scenario again. When this occurs, this cantilevering distance becomes close to 70 meters. And so this part is sagging, and we can look at the section of the column failure. So this is a simple rendering, simple view of the system. So when this column fails, this system overhangs, but there are also beams in this direction as well. So they are still carrying it. Now we have to do a nonlinear dynamic analysis, and what we calculated is that this level, this is a concrete structure with peak stress concrete beams, very deep, more than 2 meters, double T section. So at this point, we calculate 22 meters of vertical displacement, then this column is removed, and here it goes down by almost 0.4 meters. But we don't know whether the structure collapses or not. We have to do the analysis internally. And so this is a summary of the analysis. Well, before last, under vertical loads, the axial load carried by that column was about 23,000 kilometers in compression. And when the blast occurs, it's close to zero. Now, linear analysis, as you know in this column, does not give insufficient information. It's very misleading, so we have to do now analysis, because steam over here it's a segment, but it still carries some force on it at this point. And the reduction in the column force of the plastic analysis was not so much. So this column is still in compression. It's in compression because it's still supported from here. And there's another needle going in the transverse plate. And so we calculate these displacements, and you can see that how much difference is there between non-linear and linear analysis. And so if there's a collapse mechanism, you can only see this by doing non-linear analysis. Now, what we can summarize from our analysis is that roof truss remains linear elastic. It's amazing. These trusses are very strong. So roof truss remains linear elastic. None of the members in the roof truss exceed capacity despite this much deflection at the end. And upper column remains in compression, so it's still simply supported from here. And now the activity develops mainly in the D level, this level that goes huge peaks. So we need some rotation capacity over there so that they can still maintain their stability. And the system does not collapse, mostly due to overstrength design. This overstrength comes from seismic design. So if this was not in a seismic region, there would not be so much overstrength in the system. But that overstrength keeps the system at least not collapsing but partially sagging. Of course, this can be considered as a failure because you cannot use the airport at this condition. You have to evacuate it, it's a plus or minus. But there is another effect, secondary effect, which is more dangerous. This is the slab. This is a typical slab that explosion occurs somewhere here around this column. And then this slab is subjected to a huge pressure from underneath. This pressure is so much. And it becomes like an umbrella. It just pops up. Very suddenly. And because of that pop-up, the acceleration, the maximum acceleration calculated on this slab is 40 G, 40 times the gravity. So everything just fragments and goes away. And this slab is the departure of the slab, so there are so many shops, three shops, people are working on it. There are also some planted flowers, not so big, they all go up, and people may be just buried up. It's just more dangerous for the slab. I'll not show the results of this analysis because there should be some changes in planning so that it doesn't happen. But it's just this 40G is scale. It's so much, and this slab, of course, does not remain in place. It's fragmented, and each fragment goes in all directions, slightly different. So I'll not go into so much details, just expressing how severe is the problem that we have. Maybe we can get some conclusions by looking at such a rare problem that we have. So large, slender public buildings, such as airport terminals, are prone to terrorist attacks. It's the best place to attack because of the reasons that we have discussed. And it is prudent to check the worst-case scenarios for ensuring public safety. I think this is what engineers and architects should do during planning the structure. What if such an attack cannot be stopped and occurs? Can we save our structure and save people using that building? And if blast risk is considered at the initial design stage, damage consequences can be much less severe. So this is what is done now in certain terminal buildings, which I'm working as a consultant, how the traffic can be diverted and not entering into the building, or how the critical elements can be kept away from such potential attacks, and such as preventing traffic underneath the building. So this is the results that we get, actually proving that the structure does not collapse entirely was a relief, but it was not enough. It shouldn't happen anyway. So there are many things to go back and replan the structure for preventing this type attack to the building. So this is all I'd like to present at this point, and I wish, as the first speaker of the conference, a successful event for the Jordanian committee. So thank you. Secretary.
Thank you, Professor Sujolo, for this interesting presentation. المايك مش شغال. شغال؟ ايش؟ هذا مش شغال. طيب.
شغال هلا؟ أنا الثقة صاحب
مش خرج هندسة، يعني هذا المؤتمرات ديفوس الاقتصادية اللي بيقعدوا فيها سياسيين اقتصاديين ضلوا يقرروا وحكي فاضي ما له لزوم. يعني احنا كمهندسين عندنا معادلات وعندنا مخططات وعندنا برامج، يعني الواحد بده يشرحها. الترتيب السابق انا بحكي لنا قارئ حقيقة ترتيبنا العادي الكلاسيكي كثير افضل من هيك. Anyway, thank you, Dr. Harouk, for the interesting presentation. And yeah, now the floor is open for discussion. So please, if you introduce yourself, and then I'll give you the. Come over here, please. Yeah.
My name is Dr. Khan, and what a nice beginning of this conference with this example. I have two comments and one question. The first comment, I'm very glad to see that preventive damage should supersede construction. So to receive the precautions at an airport is trying to prevent damage. This is much more important than trying to make the construction after damage. And trying to combine these two is a very nice beginning of this conference. The second thing, so much similarity between airport design and between glass building. The glass transfer through the length of the column exactly like attenuation relationships. It has a dynamic analysis exactly like airport building. It needs redundancy in the system exactly like airport design. So we can try to do some research in glass building to synchronize it with airport design. My question, Professor, the more we make less assumptions, the better our readings are. I saw your column based on the top. In a structure, when you put it within the structure has no bracing. So why don't you do the analysis? I don't know if the software has limitation. Why don't you do the analysis of the column subjected to plastic building within the whole structure? The whole structure, you put the structure, yes, the glass building on the column, and you see the results instead of putting an assumptions of the upper part of the column that is placed. In a structure that does not need to be placed.
Yes, it's very difficult. I agree. Well, because then you have to, your program should be capable of removing elements, which is quite difficult. So that's why we did it stage-wise. It is correct, but quite difficult. Maybe, but it can be done. Given the time and capacity, it can be done.
Thank you, Dr. Very nice work. Thank you.
شكرا لك.
Any more questions, comments? No more questions?
Everything was very clear.
Yeah, I think so. Yeah. It's very interesting actually, and yeah, please. تفضل.
Thank you very much. You are welcome. Your lecture is very interesting, use of word. Number two, you are talking about the glass itself, how it happened, what is the effect of this glass in the structure, and take example as a follow. My question is about the bombs itself, how much its intensity, from which it consists, how can we
talk about the TNT.
Yes, that's nice. Actually, we are using the knowledge developed during the Cold War. These are usually NATO knowledge, how blast can be calculated, etc. After the Cold War, we thought that the world will be very peaceful, but it seems that it's not. So you have to make an assumption. Here, I took 200 kilograms of TNT, and so these functions can be generated, that the pressure waves. But of course, there is no limit to that. Now, explosives can be produced from pesticides. So you can find information how to produce a bomb through the internet. So it is more dangerous. But you have to build up a scenario and then go through that. That's the only thing that.
Another question, excuse me. What about the simulation between the earthquake actions and the blast? As it before,
yeah, the earthquake is much more innocent.
Some simulation.
Well, an earthquake is not too different, but blast is very fast. It's very fast, so you have to have, you'll be using very small time increments, and accuracy is more important in blast response. And the overall structure, so there's fragmentation during the earthquake. Until collapse occurs, the building is all together. But in blast, once the blast occurs, then a certain part of the structure is gone. So that's why it's difficult. And there are, well, this is only the pressure effect of the blast. But if a missile, for example, is thrown, then it has other effects as well, like penetrating the system, etc. And this subject was always thought to be the problem of protective design. And protective design is for protected buildings which can be attacked by a warplane or something like that. So terrorism is not considered so much in the past. So it's a new problem. These are civil structures. These are not protected structures. They are all in front of us. And we see the structure altogether. There is no protection at all. That's why they are very vulnerable, in my opinion.
Thank you very much. Thank you.
Yes, any more questions?
There is no more questions.
Yeah. تفضل. خلي هون ما في مشكلة. تفضل.
You talked about the blast on one column. What is the effect of the other columns and when the section, especially on the facade?
Yeah, that's, well, this column
in the
is...
airports, usually we have very high facade.
Yes.
So what will be the section there and its effect?
Suction?
Yeah, there will be a section also.
Yes, it is less actually. Well, you have to pick a column. This was the most critical one. But there are so many of them. Well, there can be a worst case scenario that two columns can be attacked at the same time. There is no end to it. But this is just one attack at one column, which is the most critical in the structure. So it's very close to the overhanging part, which may cause stability. So this is sort of considered in our scenario. And suction effects are more on surfaces. The surfaces actually has an advantage because it's circular. If it was a flat surface, then pressures are higher. So round surfaces are always advantageous in reflecting the pressure.
Yes, please.
Thank you very much.
الموضوع مهم خلينا شوي اعطيتنا وقت شوي تفضل لهون تفضل لهون ممكن تيجي لهون تفضل تفضل قرب على
What can you do to prevent collapse from a blast? Like, what's the intervening techniques to really protect the structure from total collapse? This is one question. The other, a lot of tensile structures are used in airports. The method of tension and compression on a roof. Is there a way that we can have more rigid structure or to put elements to prevent full collapse
Yes.
or complete operation?
About your first question, actually, there's not one answer. There are two variety of consequences of an attack. It can be at different parts. So, but there's no end to it. So we have to pick up the worst case and then study that. But it may occur at different parts. Strengthening is up to a certain level. Yes, if you have a weak link and strengthen it, then you can solve the problem. But it's not like that. One link activates another, so it's not, I think, possible. Well, the first defense is to prevent it. So the explosive should not approach, should not enter the building. But yes, this is difficult. There are too many human factors in it. There's a huge area of airport security. There are such thick handbooks of airport security. How it can be prevented. From structural point of view, we just accept that it cannot be prevented. If it cannot be prevented, what happens to my structure? That's our problem. And well, strengthening, yes, but in what ways it's very difficult. First of all, we have to make a good analysis. What happens? What we see. So it's a sort of tailor-made problem. Each structure has its own properties and they are affected differently. But airport structures, terminal structures have, as you see, very similar features. Usually, large spans, and we thought that the roof structure will be affected most, but those trusses are there 2 meters deep. They have enormous capacity of carrying weight. And after such displacement, roof structures was linear elastic. I wasn't expecting that. Even the column, the low part of the column goes probably the roof structure may work in tension and carry some part of the structure below. So it's a strong system, but it's sort of over-designed.
Can you use some diagrams?
No, that was not nice. Yes.
Anyone? Yeah, Tobin.
Thank you very much for a very interesting presentation. My name is Riyad Al-Mahidi from Swindon University in Melbourne, Australia. My question is in regard to the probability of failure rather than a deterministic approach, given the fact that we have a multiple column situation. Wouldn't it be more applicable if we expose the individual columns to glass and look at the probability of failure of the entire floor, the entire building, and then build up fragility curves for the designer to be able to, whether to strengthen the building, to strengthen the columns, and which columns have to be strengthened. Thank you.
Yeah, it can be done, fragility. Maybe this is for individual building-specific fragility, not for all of them, not for the entire typical buildings, but building-specific fragility, I think, can be done. So then the owner of the building or the investors can know what happens in what type of blast attacks, terrorist attacks in the building. So it's a very useful knowledge. It's very useful knowledge. And actually, in that type of scenario, also the downtime of building should be considered. If a blast attack occurs, how long the structure, the terminal will be out of service. It's a huge loss of money. The ones that we had in the recent years were not to that level. In Istanbul, it was just an outside attack. In Brussels, it was at the checking area, so it didn't affect so much area. Just the downtime was not that long. But think of an airport, which is out of service for 3 months. I think it will lead to bankruptcy. So nobody can tolerate it. So there are such monetary economic consequences as well as the structural human consequences. They should all be considered. I think it's a very good point to work on. But it should be, I think, building specific for each.
Dr. Maluk, I don't know, I have a question, I don't know if it is related or not. The event of 9/11, that's airplane, that structure and these things. And I read so many analyses and many comments on that thing, and really we don't know the fact or whatever happened anyway. But is there anything, an idea of, I mean, is that like what you're talking about, the plants also, that the plane hitting that structure, you see the structure that it affects, do you have an idea about that?
No, it's very interesting, since the plane, a terrorist plane should not go that far and just come back and attack the airport structure. In case of 9/11, the twin buildings, twin towers collapsed because of fire. Not because of
not because of
the impact, it's because of fire, but in such a structure also its impact is huge. If the plane crashes into the airport, there are lots of open places. It will be very destructive, very destructive. So it's another hazard. Another hazard. It's upper level, one level up.
And directly use the deformation ratios, diamond deformation ratios, to robust to visualize the performance of building. Of course, for this purpose, we should do some assumptions and simplifications. If we talk about the assumptions, we use equal displacement approach to find out displacement diamond, and we use damage deformation ratio as damage indicator to visualize the performance of building. And these are the two assumptions. 10% and 67% of the plastic deformation ratios considered as immediate occupancy and life safety performance levels for this study. Of course, these are not essential. They can be changed. For instance, if you think about Eurocode, they can be changed as 75%, and immediate occupancy can be constructed as yield point of the building. Here is our calculation method about the deformation ratio. We can see from the equation that we should find out the displacement diamond, and we should find out the building capacity in yield and ultimate level. And these will be used in performance visualization. As we use equal displacement approach, we can calculate the inelastic displacement shown in this equation. But in addition, this is the figure illustration of this calculation, we can use some similarity between these triangles. If we use these triangle similarities between these triangles, we get this equation. And in this equation, right side of this equation, we get Ry. This is actually the strength reduction factor for the building. So we also know we can simply doing mathematical operations, we get this equation. In addition, we have ductility is the ratio of ultimate displacement and yield displacement. And this is our second equation. If we place this equation to our diamond ratio, we get much more simple equation. So we need to calculate two parameters to visualize the performance of building. One is the strength reduction factor, and the other one is ductility of the building. First of all, we should start from reduction factor. As precast buildings are constructed hinge connections, they can be considered as single-degree buildings. So if we try to perform Peugeot analysis, we get this capacity curve. In elastic slope of this capacity curve, we can find out the stiffness of the building by dividing base shear and yield capacity of the building. As we want to find out the stiffness of the building, we know section of all individual columns. So simply we can calculate, as they behave like cantilever beam, they can be calculated, the stiffness of individual columns can be calculated with this equation. In this equation we can do some simplifications, of course, or assumptions. For instance, in order to calculate effective moment of inertia, we can say that it's 20% of gross moment inertia. In addition, we know that there are high quality standards, so the compressive concrete of these buildings is higher than 25 megapascal. So, by calculating each individual stiffness, and if we sum all individual stiffness, we get building stiffness. So we can put this to this equation. Then we need yield displacement of the building. For this purpose, Palange and Chanel has proposed this equation just for precast industrial buildings. So we can, this is a simple equation, and we can use this. And with simplification, we can say that we can calculate each individual column yield displacements. And if we take the minimum of this yield displacement, we can say this yield displacement is the building displacement capacity. So if we also put this equation to here, we can get base shear capacity of the building. Then we also need to calculate period of the building. This is also no question. We need the mass of building and stiffness of the building. And we already calculated the stiffness of the building. So if we put this equation, then we get period equation more simple way. And we know the parameters of this equation. For ductility, as we know the strength reduction factor, these are the main calculations, we can also determine the ductility of building. We can simply, of course, analytically, we can do Peshawar analysis, and we get the capacity curve, but we need to calculate ultimate displacement capacity of the building. For this purpose, Palange and Chanel and some other studies can be used, but these all studies will increase the computational efforts. To make it more simple, we can use intuitive way, but of course in a systematic approach based on experiences and some analytical observations of some studies. For instance, Chanel and Palange has determined that the ductility of these buildings mainly range between 1.5 and 3. And then Chanel et al. Has described that we can divide these buildings as high ductile and low ductile, and they say 2.5 can be used to distinguish these low ductile and high ductile buildings. And recently, Palange et al. Has defined average ductility values for high ductility and low ductility buildings. So, intuitive way, we can use these values also. As we described the determination of strength reduction and ductility of building, we can apply this method to existing building. This building is existing in Denizli Organization, and these informations are provided by Palange and Chanel. And we can see some properties of buildings. Building elevation is 8 meters, and girder length, purlin length, number of purlins, and more details can be found in this study. And there are also common features which we will use in this method. As we can see, precast columns mostly square sections, have square sections, and each section is given here. Longitudinal reinforcement ratios and volumetric transformance reinforcement. Here we should note that Palange and Chanel defines this volumetric transverse reinforcement ratio as moderate. Why we say that? Because ductility of individual column is important in determining the ultimate displacement capacity of buildings, because these buildings are constructed as hinge connected and partial collapse is important in these buildings. So individual member displacement capacities is important also. So we can apply the method simply. As we know the sectional dimensions, we can find out the gross moment of inertias and effective inertias also, as stated in the table. And we can find individual stiffnesses also, shown in the table. Okay. And if we sum, we get the stiffness of the building. And if we calculate the yield displacement of individual members, as we stated, we should take the minimum of the yield displacement as building yield displacement. And the other calculations are shown. As we know, the stiffness of the building and the displacement capacity of building, so we can get the base shear. Building mass is provided by phalangeal channel, but can be found by doing vertical analysis by adding deep and lead loads. And as we get stiffness of mass of building and base shear of the building, we can calculate the period of building. To calculate the strength reduction factor, we need to calculate the seismic scenario. Seismic scenario was given by phalangeal channel. To make a comparison, we take the same scenario. In the scenario, maximum acceleration was taken as 1g, and two different scenarios was taken as local soil side and soft soil side. Using, if we implement our capacity curve in this diagram, we can get the specular acceleration at our period of building and yield acceleration of our building. And if we put in this equation, so we can get strength reduction factor. So these are the capacity related parameters in our method and compared with analysis and rapid estimation method provided by phalangeal channel. In here we should mention this value because we find this value with intuitive way. As we stated earlier, phalangeal channel says that these members have average confinement. So considering this, we consider the study of Senal and phalangeal. Phalangeal says loaded pair buildings as 2.1, and Senal et al. Stated that 2.5 can be used to distinguish low and high ductile building. So if we take the average of these values, we can get the ductility of this building. And you can see that this is very close to analysis. And also we should mention that this study and rapid evaluation methods gives the similar yield displacements. Okay. We also compare the scenarios here, or damage deformation ratio, with both analysis and estimation methods. We can see they are very similar. And we also made exceptions that 10% and 67% of the plastic deformation ratio is our immediate and life safety performance limits. So we find out before our deformation ratios. So in this case, our building in first scenario is moderate, and this is also similar with analysis and estimation method, rapid method. And in the second scenario, it's also, they give the same performance of the building. So in this method, in rapid evaluation method and analysis methods have same results. So I will not tell about so much, we can find it in equation, but simply we should say that this is a recommendation. Although indicated method have good agreements, we should also improve this method to other buildings, and we should apply to other type of buildings in terms of structural characteristics. Thank you very much for your attention.
Thank you very much. Thank you very much. We give only one, if there is one question, because we are running out of time. One question. Okay, thank you very much for your lecture. So we are going now to the second lecture for Sika Minarno. If he's here. The second lecturer is Dr. Sika Narno. His paper titled 10 Years After the Java Earthquake, Post-Reconstruction and Earthquake Resistance Housing. He is from the Civil Engineering Department, University of Islam, Indonesia lecturer and head of Innovation Center. PhD degree in Construction Management, Sheffield Hallam University, UK, in 2007. Research in building material and disaster management. Please present your paper.
How many minutes?
15 minutes.
15 minutes.
Yeah, 15 minutes.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Okay, I introduce myself that I am from Indonesia, and you know that Indonesia is very big country, that we have 17,000 islands, and the population is about 250 million people over there. And at the moment, of course. Sorry. Okay, today I would like to present about the Java earthquake when it happened in 2006, and then I would like to have a preliminary analysis after the construction phases after the earthquake for the houses only. This is the earthquake happened in 27 May 2006. You know that 150,000 private houses totally destroyed, and 200 units and with 5,700 deaths. You know that this is Indonesia with supermarket of disaster. Yeah, earthquake cannot be prevented. It is given by God, but much of the damage caused by earthquake is preventable and preventable. It is why predicting earthquake may be difficult, but preparing for disaster is not. This one is case of non-injury causes. What happened in Indonesia? All of this non-injury building collapsed during the earthquake. This is non-injury cause. Our causes were masonry construction with or without reinforced concrete frame, in particular those built by medium low-income communities or medium low-cost housing. At the moment, the typical of damage and collapse like this, and the moderate damage like this. The official reconstruction during 3 years during 3 years after the earthquake, 2006 till 2009, it's incredible that 200 houses were already reconstructed during 2 years, during 3 years. In Patalan village, 193 investigated houses totally in accordance with safety standard, which there were 19 houses with very good quality and 74 houses of good quality. During 2 years, all the reconstruction houses is conformed with earthquake standard. The technical intervention is quite good at the moment. The detail in column join is very good. This is the simple house after reconstruction, official reconstruction. Up to now, let's look. Yeah, this is 10 years. I have surveyed 200 houses. After 10 years, we come back to the normal life. No concept before. People build on their own fund. Many ignorance of the safety standard for this due to the limited budget, due to the economic pressure. It is true that poor in design and construction right now we come back to the before design. Segregation and honeycombing is common. Incorrect beam and join is a real one. Let's have a look at this one. This is the beam segregation. This is the column. It's not happen when in the official reconstruction, but right now in normal life, we found a lot of this one. And then we have survey. This study is primarily assessment why the current implementation of public standard for house reconstruction is hard for the last 10 years. The method, I collect 200 new and extensive houses situated in 7 districts, and the homeowner with very big background have been interviewed. And a focus group we held why the problem occurred, why the finding took place. This one, the findings. 85% of reconstruction costs after 10 years is a bad in implementation of seismic features, seismic standard. Let's have a look. Very good, it is only 1%. Good is only 4%, and the last one is the majority is bad in implementation. Why? This is the big question for us. Yeah, the problem is that the problem is not the technical intervention. The previous presentation talked about the complicated mathematics, but in this presentation, in this article, in my mathematics, it is about not the technical intervention. It is about the channel of dissemination. The importance of dissemination message. Yeah, to achieve sense of control and sense of ownership. If people rationalize that the implementation of seismic features in their own house is most effective strategy for reducing losses, at the same time they perceive it is practically possible and achievable, they can control it. But it is very low right now. Yeah. After that, they can also achieve sense of ownership. It is why the first method that we how to improve safety standard in common houses in Indonesia is make a culture of prevention by sense of control and sense of ownership, not in technical, because in technical we have a lot of book that present how to make simple houses with earthquake resistance. And then the role of government is that government should enforce safety standard through the building reconstruction permit. I understand that right now in Indonesia, a lot of new and existing building, there is no permit, there is no construction permit. Because the limited number of engineers who can involve in the construction in house, common house in lay people. I think this one that I can reveal why the implementation of safety standard is quite good. Its conclusion is the balance track between communicating local seismic risks and importance of seismic codes to the people and enforcing them to implement the codes while some intense regulation is imperative. It should be not prescriptive. We have one strength in Indonesia. We have community-based reconstruction. The Japanese self-help culture as gotong royong. People can come together, join together, build a house. The other time, people come as well together, build house together. Yeah, this is the most strength in Indonesia. Thank you very much.
Thank you very much for your lecture. We open for one question. If you have any questions, please.
Thank you for a very interesting presentation. It used to be that with the massive amount of disruption that occurs on simple structures like these, and as you mentioned in your lecture, education is crucial for people to understand what the risks are and what the disasters that would happen. People are not going to understand codes and standards in these parts. What's required really is simple pamphlets to show drawings, simple drawings of what it should be like. I mean, if you go there and say, okay, this is a seismic code, this is that, they're not going to buy that. So, like that one, I like that one. I like that picture. Thank you.
In technical intervention, many local engineers have developed like this. Simple standard, simple drawing that people can understand how to make their own house without any intervention from engineer, high level of engineer. People can understand how to make the house to be the earthquake resistant. And we can produce from internet, we can have a lot of article brochure in government institutions. But the problem is not the technical like this, but how to make sense of control on the people. How to make that this house is belong to us, belong to the people, that if the disaster comes, the house will stand from the earthquake. It is the hard point, rather than the technical like this. Thank you.
Thank you. Thank you for your lecture. Now we will go to the third lecture. Engineer Muhammad Zaidan. And the second one is Wael Rifai. Muhammad Zaidan Engineer Mohammed Zaidan, he will represent the paper. Engineer Mohammed Zaidan, his paper is nonlinear analysis of steel frames subject to seismic forces. He is from Tijla Establishment Construction Contracting from Jordan, project manager, education, MS in structural engineering at the University of Technology, Iraq, Baghdad, وبيس from Saddam University, Iraq, Baghdad. Experience, Tijla Construction Contracting Establishment Project Manager, 2005, Associated Consulting Engineers, Consultant Engineers 2004-2005 وسبيل الهندسة Consulting Engineers from 1999 to 2001 والموبل Contracting Site Engineer from 1993-1999 Research interest in infrastructure design, construction engineering, construction management and green buildings. So please present your paper.
Assalamu alaikum. The title of our paper is Nonlinear Analysis of Steel Frames Subjected to Seismic Forces. In this paper, nonlinear analysis of steel frames subjected to seismic forces is presented. The analysis adopts the beam column approach. The formulation of the beam elements is based on Eulerian approach. Changes in number core length due to axial strain and flexural points are taken into account. A modified tangent stiffness matrix which takes into consideration the geometrical nonlinearity is used. A special form The objective of this paper is to derive the equation of motion and deriving a modified tangent stiffness matrix in global coordinates, which takes into account the geometric nonlinearity. The load comes from the base motion due to earthquake is added to static load. In this paper also the beam column element is developed by using a beam column approach in formulating the elemental using force displacement relationship. The basic stiffness matrix obtained is transformed into the element stiffness matrix by coordinate transformation since the incremental Newton-Raphson solution technique is used. The element stiffness matrix is presented in the incremental form to facilitate the numerical implementation. The following assumptions are considered in the modeling of the beam column element. 1. The member is prismatic and plane section before the formation remains plane after the formation. Second, all the large rigid body displacement are allowed. Relative member deformations are considered to be small enough to justify the use of beam column theory. Third, influence of axial force on member stiffness is taken into account. Number 4, effect of flexural moment on axial stiffness is taken into account. 5 assumptions. Changes in member core length due to axial strain and flexural point are taken into account. The text loads are applied only at joints. In extending the method of beam column approach to the dynamic case, the masses are assumed to be lumped at the joints only. The numerical step-by-step integration techniques has been used for solving the equation of motion. This technique extends itself to solution of base motion response problem because the incremental nature of the behavior associated with time-dependent time stresses. Within a given time step, the acceleration is assumed to be varied linearly. The deterioration of stiffness leads to increase in deformation, leading to the development of large secondary force due to geometric nonlinearity, and in many cases leading to instability and failure. According to that effect, excessive deformation have been introduced as the delta effect. Modeling of earthquakes. In this present investigation, earthquakes was represented by substituting the term F of T by term mass multiplied by second derivation of time initial plus force of time initial at the initial time of earthquake. Then these internal forces and displacement at time t of I plus 1 or t of j m multiplied by second derivation of t of j plus f of t of j at time t of j, and so on to the end of the earthquakes to get the final forces and displacement. To make the analysis of nonlinear problems of structure more easier, two static computational techniques were used in this investigation: linear incremental method and nonlinear incremental method. The method of nonlinear method is similar to linear method in both applying loads in small increments and then calculating the change in displacement caused by each load increment. The difference between the two methods is in the way of determining incremental displacement. It is shown that for linear incremental method, numerical solution tends to drift away from the exact solution. This method requires smaller load increments than those needed when we use nonlinear incremental method. We used for loads, all frames were subjected to identical loading conditions. Loading conditions and seismic loads. The design floor bed loads were about 35 kN per meter. Design flight loads were 17.5 kN. Exterior wall loads were 6 kN per meter, which contribute a total of 50 kN to each exterior wall at each floor level, and design wind loads were 12 kN per meter. A load combination factor of 0.75 was applied to the combination of gravity and wind loads, which is consistent with the AISC specifications. For frame configuration for this study, to ensure the greatest utility of results, it was decided to limit the range of buildings dimensions, as in the rear buildings, for the building dimensions to include building sizes most likely to be encountered in current particles. The range of buildings height from 1 to 10 stories at 3.5 meters approximately per story, and building width at 4 to 6 meters per bay. All frames were spaced at 7.25 meters, centered in plane. All column bases were considered fixed. To this end, it was decided to design 15 steel frames, with some of them having a single bay or double bay, while the others with 3 days, as in this table and this frames. Now our assumptions. Our parametric studies. A number of choosing parameters are studied in this section. Number one, effect of large displacement on the behavior of steel frames subjected to seismic loads. This the effect of change of geometric structure, second order geometric effect of the behavior of steel frames which are subjected to seismic loads is investigated. It should be mentioned that the term of large displacement means that nonlinear equilibrium equations must be written for the deformed configuration of the structure during load processes. To this purpose, different steel frames were analyzed by computer and without considering the nonlinearity. It may be noted that from the figures that the horizontal displacement increases as the effect of large displacement is included in the analysis. Second parameter, effect of number of stories and number of bays. The effect of number of stories and number of bays on the fundamental period of structure, which are a function of many parameters, is represented in this section. All 15 frames have been analyzed with considering fixed end conditions. It can be concluded that the fundamental period increase with increasing of number of stories, as in figure 10, and number of bays also. Also, it can be observed that the horizontal displacement increase with increasing of number of stories, and decrease with increasing of number of bays, as in the figure 11. The third parameter is effect of time step size. The influence of the time step size on stability and accuracy of the solution is presented for the series of tests made using various time step intervals. These time step intervals were chosen to give responsible practical range of stepping. Fourth parameters, effect of static loads. Static loads are almost associated with the mass which is placed on or in the building. This additional mass can be beneficial to the structure subjected to earthquake loading. The 5 parameters, the effect of subgrade reaction on the displacement and forces of the superstructure was investigated by considering different values of subgrade reaction. The 6th parameters, effect of earthquake duration. The effect of earthquake duration on the behavior of the structure is represented. 3 durations are considered in the analysis of different frames. It may be concluded that the earthquake duration has a small effect on the behavior of the structure, especially with the earthquakes which have long durations, as in the figure shown. The conclusions. Briefly, based on the results obtained in this paper, several conclusions may be drawn. These may be summarized as follows. 1. This investigation shows that the large displacement in elastic behavior of plain steel frames subjected to earthquake can be accurately predicted using the beam column approach. 2. Considering of large displacement in the analysis decreases the ultimate strength of the structure by a percentage of about 10%. Fundamental period the fundamental period increases with increasing number of stories and number of bays, and increasing number of stories tends to increase the horizontal displacement, while the fundamental period decreases as the number of bays increase. Number 4, the influence of existing static loads during the analysis of steel frame structures subjected to seismic forces is small during the earthquake duration. Number 5, table and accurate results in the dynamic analysis are affected by the selection of the time step size. The 6th and final, the dynamic response of steel frame structure is substantially affected by the values of subgrade reaction. Thank you.
شكرا المهندس محمد زيدان. في أي سؤال؟ أي question؟ نروح للمحاضر الرابع. لا في أي سؤال للمحاضر الرابع؟ سؤال؟ تفضل.
أنا المهندس عثمان. عندي سؤال بس عن البي داتا افكتس في النون لينير اناليسيس اند لينير اناليسيس. انت بس حكيت عن البيج داتا رايت؟ سو هلا بالنسبه للسمول داتا هل التاثير يختلف بالنسبه لللينير والنون لينير اناليسيس؟
بالتاكيد يختلف. بالتاكيد يختلف، بس هذه البيبر ما اخذنا غير اللارج ديسبيسمنت اللي بيصير عندنا نون لينيرتي. بس هي الحقيقه بتختلف بشكل كبير
يعني بس انا اسف، بس هل تاثيرها كبير؟ يعني هل تاثيرها بياثر كثير على النون لينير اناليسيس، وهل هي نفس التاثير بالنسبه لهم الاثنتين؟
التاثير اذا في اللينير انكريمنتال ميثود او في اللينير ميثود اللينير اناليسيس اخذت سمول ستيب سايز مور سمولر ستيب سايز ما راح يكون في تاثير، بس اذا كانت نفس الستيب سايز في اللينير والنون لينير راح يكون في فرق.
شكرا.
عفوا.
شكرا. المحاضر الرابع هي محاضر الورقة مشتركة بين اثنين، البروفيسور مؤيد النصرة والدكتور محمد داوود. برزنتيشن محمد داوود. العنوان Study of the Transitional Shift Between Place and Shallow Shells. Institute Global Engineering Consortium, Professional General Manager, PhD Structural Engineering, Research Interest, Optimization, Material Assessment. تفضل دكتور.
السلام عليكم. بسم الله الرحمن الرحيم، والصلاة والسلام على سيد المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. أنا في البداية بدي أوزع عليكم كلكم سماعات عشان تسمعوا بالعربي. فراح تكون المحاضرة بالعربي عشان ما نذكر الأول. القضية اللي بنحكي فيها اليوم هي العلاقة ما بين البلاطات، حنحكي عنها بلاطات اللي سلابس، سلابس البلاطات المسطحة، وما بين لما تاخذ الشكل الدايمنشن الثالث او البعد الثالث لما تصير قبه مثلا، اذا بنحكي عن بلاطه دائريه او اذا بنحكي عن بلاطه مربعه او مستطيله لما تصير عندنا فوق البليت او بنحكي عن نوع من انواع المطويات يعني فيها بعد ثالث. الفكره هي انه بنحكي رح نقارن ما بين سلوك البلاطات حتى تتحول الى دوم والى قشريات، يعني بانواعها ثلاث: البلاطات الدائريه والمربعه والمستطيل. هلا مفهوم ترانزيشنال شيفت هو نحكي الارتفاع الانتقالي، يمكن اسميه انا، ممكن اسميه تسميه اخرى ترانزيشن رايز، ممكن تكون افضل شوي تسميه. هي الفكره انه احنا اذا بنشوف هذه البلاطه الدائريه بهذا المكان هي بلاطه في الوسط، يعني مستقيمه مستويه مسطحه، وبدانا نرفعها من الوسط. شبيان كنا رفعناها حوالي 5 سم. هل تغيرت؟ هل صار في فرق ما بين هاي البلاطه رقم 2 والبلاطه رقم 1؟ هاي البلاطه اللي هون والبلاطه اللي هون، هل في تغيير متوقعين بالسلوك؟ طب لو رفعناها كمان شوي، يعني كمان مثلا 10 او 15 سم، هل راح تضلها بلاطه ولا راح تبدا تاخذ صفات نحكي القبه شبه يعني شبه السطح؟ راح نضل نكون بهاي العمليه، راح نكون عمليه رفع انتقاليه، وكل كانت خفيفا ناخذ كل رفعه من الرفعه والثانيه حوالي 2 سم. ودرسنا شو حيصير في البلاطه، شو راح يصير في الستفنس، شو راح يصير في الديفليكشن، شو راح يصير في التسليح، الستريس، كل هاي اندرست حتى اني اربط انا متى نحكي لها بتشرح ثوب هكذا سلاب فلات سلاب وتروح باتجاه انها بلشت تشتغل 3 دايمنشن. هذه هي الفكره اللي كانت في الموضوع، يعني تابعتها لحد ما صار كانت صفر، يعني زيرو رايس، يعني نحكي لما صارت فول شيء اللي هم تبعنا في السلوك، نربط يعني نمسك النقطه اللي بصير فيها التحول في السلوك لهذه الوضع. يعني بعض التعريفات الموصوفه يمكن هاي الرسم توضح شنو ملح الاسلام، ممكن نحكي الأردني والهسبان او نحكي الليث او الاسلام، ممكن نحكي مصطلح الديناميكا والاسلام اذا بنحكي عن سيركل الاسلام. المبدا صحيح او الفكره اجت من نظريه احنا بنسميها نظريه سمول ديفليكشن ثيوري، هذه النظريه العاديه اللي ناخذها احنا كيف نحسب الهبوط من الاحمال ومن الابعاد من الماتيريالز مثلا، اي النظريه العاديه اللي متعودين عليها، والنظريه الثانيه الصحيحه اللي هي بتبدا تصير مشابهه لموضوعنا اللي هي اللارج ديفليكشن ثيوري. هلا لما بصير عندي مثلا عندي بلاطه وصار فيها هبوط كبير جدا تبلش تاخذ البعد الثالث، يعني اذا عندي نزله 2 ملم او 10 ملم او 2 سم بعدها بنحكي عنها بلاطه، لكن اذا نزلت مثلا 10 سم هبطت 10 سم ناخذها بنلاحظ انها تكتسب قوه اضافيه. هاي الوحده تصحيح الظاهره، وبالتالي احنا يعني من هذا المنطلق يمكن درست هذا الموضوع. هذا مقارنه بين سلوك كبلاطه عاديه مسطحه اللي هو اللون الازرق اللي هو سمول ديفليكشن ثيوري، واللون الاحمر اللي عندي انا اللي هو اللارج ديفليكشن ثيوري. اذا ملاحظين احنا كل ما زاد الديفليكشن عندنا كل ما زاد تحمل الاحمال، يعني الحمل بيزيد، كل ما زاد الديفليكشن كل ما صار عندي البلاطه اكثر تحمل للاحمال. يمكن انا هيك حاولت اخذ علاقه مشان افصل السلوك ما بين البلاطات وما بين القشريات. اذا تلاحظون في البدايه لما يكون تقريبا في المستوى الادنى من الارتفاعات او من الديفليكشن الاثنين بيتصرفوا نفس الشيء، انا بيبداوا يفترقوا بشكل معقول لما يزيد الديفليكشن، يعني لما يزيد الهبوط لنا بنلاقي صار في فرق في السلوك واضح. حاولت افصل السلوكين مع بعض بعكس المعادله، بدل ما كانت علاقه الحمل اخذت معكوس الحمل، اعطتني حقيقه سلوك واضح في الجزء الاول من المنحنى اللي انتم شايفينه هون. هذا الجزء الاول اللي بيمثل سلوك البلاطه، والجزء الاخير هون اللي هي بنروح حوالي انفينيتي ستيفنس تقريبا لما نروح للفول شيب. يعني اثنين واضح، الاثنين اللي هون سلوك واضح جدا من اتجاه الشمس، لكن هون عندي سلوك واضح من اتجاه البعد. لان المرحله الانتقاليه اللي بدرسها اكيد بينهم حاولت انها تكون شيء زي، يعني هذا الكيرف بيمثل وهذا المنحنى الاول بيمثل لنا البلاطه، هون المنحنى الاول، المنحنى الثاني هذا التقائهم هون هي النقطه اللي انا ببحث عنها، اللي هي بتمثل شفت بين السلوك الاول او الانتقال بين السلوك الاول والسلوك الثاني. يمكن احنا اشتغلت انا فاينايت موديل لمختلف انواع البلاطات، زي ما حكيت لكم كنت اخذ يعني البلاطه اخذها من الصفر، من ارتفاع صفر او من هبوط صفر لما توصل لفول شيب. طبعا انا يعني بدل ما اخذ هبوط واقارنه اخذت الان اللي احنا بنسميه اللي هو جيومتريكال شيء، ما صرت اخذ بدل الهبوط صار عندي راس جيومتريكال راس، لان هيك شكلها جاي من الاصل مصموم لهذا الشيء. يعني الحقيقه هذا النوع الحقيقي مش نتج عن انه في احمال عملت هذا الهبوط اللي صار شكلها طبيعي بهذا الشكل. درست في عده انواع من الاحمال على البلاطات الدائريه، اخذت اذا كان عندي ميكرون ديستريبيوتور يعني حمل موزع او حمل مركز او حمل دائري، يعني نوع من الاحمال المتوقعه لاستخدامات البلاطات من هذا النوع. درست انواع مختلفه من الاحمال، درست كمان اثر لو الانتنسيتي فلو، الانتنسيتي فلو كان يبدا مثلا من شيء بسيط ازيد الانتنسيتي فلو حتى اشوف اثره على المرحله الانتقاليه. حكينا انه الشيء اللي كمان لاحظناه هون في هذا البحث اللي عملته صار دائما كان علمنا احنا او الراكب شو وضع الاجهادات في البلاطه، انه دائما ما تزيد عن القدر المسموح فيه حسب الكودات او حسب احنا الطريقه اللي بنشتغل فيها او حسب ما هو متعارف عليه في العالم. اخذت انه بدل ما احكي انه في عندي حمل في عندي راس، اخذت العلاقه ما بين الديفليكشن نفس الديفليكشن، الهبوط مقدار الهبوط ومقدار الراس. يعني لو كان زيرو راس عندي كم مقدار الهبوط، لما نرفعه سم او 2 سم كم مقدار الهبوط، يعني الراس كان من البدايه من راس بسيط جدا من تقريبا 0 ملم يمكن لما بدا السلوك يثبت تقريبا، انه ثبت السلوك، لان هون استطعت انه اتاكد انه الان وضع. بنفس الطريقه استطعت اني اخذ وين المرحله الانتقاليه. واضح انه الجزء الاول هون في نحكي البلاطات قليله الارتفاع وقليله العمق او شيء صغير العمق كنا نحكي عن بلاطات، وواضح جدا في الجزء الاخير وبعدين نحكي عن شمس. وحتى درجات المرحله الانتقاليه بينهم وبعد يتغير المتغيرات كلها بنفس التاثير. هاي النقطه في ترانزيشن رايز على كل المتغيرات، كيف تتاثر بكل المتغيرات. في درست كمان الكان درست سلابس كمان نفس الطريقه، يعني علاقه ما بين الريفلكشن سنترال ريفلكشن ما بين الرايز كلها. البلاطات يمكن مربعه كمان اخذتها. يعني من بعض النتائج اللي طلعت لنا مثلا هون غيرنا نوع اللود، غيرنا نوع الحمل، كان كونسنتريتد لود عندي بعدين صار حمل دائري رينج لود، كان عندي ووتر بريشر اللي هو فاريبل بريشر، ولقيت انه الترانزيشن رايز تقريبا نفسه اللي بيطلع، يعني نفس الارقام قاعده تطلع بتغير نوع الحمل. وهذا يعني بيعطينا دلاله انه نوع الحمل مش كثير بياثر على هذا الارتفاع اللي احنا بنقول يعني ارتفاع المرحله الانتقاليه. هيك درست كمان تغيير السماكه، كل ما كانت اسمك او كل ما كانت اقل، وجدت علاقه مباشره ما بين السماكه للبلاطه وما بين الترانزيشن. كل ما زادت سماكه البلاطه كل ما زاد هذا الارتفاع الانتقالي. طبعا كمان نفس النتيجه في البلاطات سواء كانت دائريه او مستطيله او مربعه. استطعت نحط معادله صحيح لهذا المقدار الارتفاع الانتقالي خلينا نسميه. حطيت معادله بسيطه جدا اللي هي تقريبا 0.85 ثيكنس مضاف لها 105 ملم. هاي كلها ملم القياسات، او يعني بدي ابسطها اكثر، انا بحكي انه بيلزمني اني ارفع البلاطه من الوسط تقريبا ضعف سماكه البلاطه. حوالي ضعف سماكه البلاطه للارقام اللي بيتعامل فيها بسمكات البلاطات العاديه. يعني لو حد ارفعها ضعف وهي كمان ثيكنس تصير 3 مرات الارتفاع الكلي، يعني بحكي عن ثلث الثيكنس. يعني اذا كانت عندي عقده 30 سم انا ممكن استغني عنها بس استخدم 10 سم منها فقط تعطيني نفس النتيجه او حتى اقل شيء في الكلفه. يعني بالاخر حبيت بس الخص اللي عملته انا هيك في دراسه اقتصاديه. اخذت مثال، اخذت بلاطه عاديه، بلاطه بسيطه الارتكاز كمان في 4 طبعا وحدت الاحمال واخذت بلاطه سماكتها 300 ملم. حسب يعني شفت الريفلكشن، شفت الهزوم، حسبت الكلفه وقارنتها بالبلاطه نفس البليت اللي عندي، بس بدل ما اخذها 30 سم حتى 8 سم ورفعتها من الوسط حوالي 16 سم 17 سم من الوسط تقريبا حسب المعادله اللي طلعت عندي. لقيت انه انا يعني بقدر احصل على اكيد ديفليكشن اقل بكثير، مومنتس اقل، في توفير 70% في الماتيريال بالنسبه للكونكريت، حوالي 50% توفير في الحديد. وهذه صحيح النتيجه اللي يعني حبيت اني ابرزها في هذا المكان. يعني وهذا السؤال الاول اللي راح اساله عنكم، يعني ليش الدراسه في هذا المكان؟ صحيح هذه النتائج، هذه الدراسه يعني قدمناها على شكل مقترح متكامل، دراسه معماريه، دراسه انشائيه لابنيه قدمت لجمعيه المستثمرين في قطاع الاسكان، اساسا قدموها لامانه عمان كتعويض عن الابنيه اللي تقدمت في الجوف في منطقه الجوف. لقينا انه قدمنا نموذج بكلف حوالي 40% فقط من الكلفه الاجماليه للمبنى المشابه. يعني المبنى اللي كان جنبه بالضبط من الطوب او من الحجر حسب النوعيه، لقينا انه ممكن احنا نوفر 60% من البنى. يعني مع طبعا اكمال المقترح اني اخذ نسبه مئويه اضافيه وطابق او طابقين زياده من امانه عمان ونقدم لهم مستثمرين يعني ياخذوا البنايه يبنوها ويسلموها لصاحبها زي ما كانت ويبيعوا الفرقيه التسهيلات، ما تكلف الدوله شيء ولا تكلف المواطنين شيء، ويطلع المستثمر ربحان. كان هذا مجرد ان شاء الله تقدم في النهايه وتنجح وتعطي قانون سهل الجهات الرسميه. في النهايه انا بشكركم يعني على حسن استماعكم. يمكن ما قلتكم اياها وان شاء الله يكون ضمن الوقت يعني سامي يعني جاء حضر.
نشكر الدكتور على هذه المحاضره القيمه. في اي اسئله؟ دكتور حمد الله.
Just only one story building. طبعا هي الفكره هذه انا ندرس شيء لوكال، يعني هو فكره العقد نفسها الطوابق نفسها، فهي الطوابق تنطبق على كل الطوابق، يعني من 10 طوابق فهي طوابق نفس الشيء تنطبق. نعم. عملنا نظام يعني شيء يعني القضيه مش متعبه زي ما بتتصوروا، احنا بنحكي عن 10 سم او 8 سم سلاب، لما ناخذ ضعفها رايز يصير المجموع كله 24 سم، هي معظم عقداتنا 24 سم. وصغناها بشكل حقيقه يعني انه يجاوب على تساؤلك انه فعلا احنا ما راح نخسر سبيس ولا راح نخسر اي شيء، راح تاخذ نفس السبيس ونفس القوه والمتانه لكن بكلفه كثير اقل.
تاثير الهورزنتال فورسز
نعم. في حاله البلاطات الدائريه اكيد الهورزنتال فورس راح يشملوها على شكل اجهادات حركيه بنسميها موف ستريسز على اساس التنشن فورس. في البلاطات المربعه راح يصير في عندي انا قوه كمان ان بلين فورسز راح تكون كانها جسور لبعض، يعني نفس نظريه الفورمد برنسبل. لا راح يكون محتاج لانها شكلها مربع، يعني راح يكون كل جسر راح يعمل تنشن في الجسر العمودي عليه. راح يكون طرفين بتكون شيء في الجسر
دكتور سؤال هلا يعني لما نبلش الاستعمال 8 سم بعدين تصير في النص 12 سم، طب هذا بقى شنو في عندي اللود بشكل كبير في المنطقه اللي فرق
هي الفكره انه احنا برفعه بشكل حقيقي، يعني الرفع هو شكل رفع حقيقي مش ناتج عن الفليكشن، يعني هي نفسها راح تضلها 8 كامل يعني مور بيك راح يكون وراح يكون زي صحيح. يمكن زميلنا شوف مثلا راح يحاول ياخذ من المحاضره يكتب على شكل في كاستنج بس تكامل للمشروع. زي شوف بص هنا الفكرة يعني فكرة البحث كله بهذه الطريقة، إنه أنا أحول يعني احنا نعرف ممكن نحكي الوان دايمنشنال ممبر في الجسور، بعدين شوي أرقى شوي بنحكي تو دايمنشنال ستيفنس اللي هي البليتس، بعدين لا أرقى شوي اللي هي راح تكون الشمس. الشمس صحيح معظم القوى هي عبارة عن قوى من بلين فورسز سواء تنشن أو كومبريشن للشمس اللي من برينز كومبريشن أو تنشن يكون بروح تسمي برينز. الفكره انه في فكره المشروع اللي انا استفيد من بدل ما احكي عندي مومنت في عندي تنشن وعندي كومبريشن لا بستفيد اكثر بحول كله تنشن او كله كومبريشن في مثال كل الاجابات راح تكون كلها كومبريشن. بالنسبه للباوندري كونديشنز يعني عشان استخدامنا للفاينل اليمنتس يعني في نقطه من النقاط راح تكون بند وبقيه النقاط راح تكون كفرز عشان نعطي مجال للحركه الجانبيه ندخل تاثير هذه الحركه الجانبيه بدل ما تروح عن طريق السبورتس لا بتروح انترنالي من خلال النمبرز نفسها من خلال الفاينايت او الاليمنتس جاوب السؤال. يعني هي قريبه من بيز راح تكون قريب من البيز كثير جديده لان الحين نحكي عن مسافات بسيطه جدا الليفل اوف ستريسز قليل يتحمل الثيكنس اوف سلاب، لكن لما نحكي عن كونكريت سلاب
تساوي
لا مش حكينا من الإنتاج سنتر أنا هذا الإنتاج سنتر أشتغل يعني طريقة من الرامس إذا كان تقليد سؤالك نعمل أجزاء المائية على شكل الرامس لا بالتالي هي فنك الرام لا نعمل استعادة
آخر سؤال شامل
حلو
بس حسب اعتقادي ما بعرف دراسة كانها على سبب السلاح بس موضوع الاستاذ
نعم سبب السلاح
يعني احنا بين الأردن كله سلاح هيك ما بعرف كيف
يعني في الأردن طبعا رد سلاح المفروض النظام الشائع بس اسمه النظام ذكاء اصطناعي هذا الوفر الكبير من عين التفكير
حوالي 70% I think. لا المهندس السابع حكى انه كنا نسيب by 70%.
السير عالي، كان السير عالي حوالي من المجمل حوالي 60% بالمجمل، 40% من الكلفة حتى مع التشطيب السيستم هذا مع المشكلة.
شكرا دكتور على هذه المحاضرة القيمة. المحاضرة هذه المحاضرات بدها تسليم بالله عمل اسلاف.
لا هي الان بنفصلها، قاعدين بنفصلها الان، قاعدين بنعملها تفصيل حقيقه مش لعب، يعني رح تكون فول سكيل.
فعلا شغله مهمه بس البيهيفير بالنظر من تحت ما نزلت الطلاب.
لا بالعكس رح استغلناه كمنظر جمالي بالغرفه يعني.
جمالي. نشكر الدكتور، نشكر المحاضرين كلهم على هذه المحاضرات القيمه. تفضلوا على الغداء والمحاضره السيشن 3 راح تبدا الساعه 3. سيشن 3 هو الساعه 3. شكرا على حضوركم.
The last thing is the budget. We have just on bridges. We spend every year about $34 billion on our bridges, but we need to spend $77 billion annually. So we have a shortfall of 50% just to keep what we have right now. To keep one out of each bridge efficient, we have a shortage of 50%. So we're expecting more deterioration unless we as a professional, we as educators, change the mindset of our engineers. We need to work now. Okay. Do you hear me? Okay. So we need to look at. Okay. Okay. So we need to look at the economy. Okay, this is what we usually do, looking at what is the best price for our structures, but it doesn't work anymore. We need also to look at the community. There are more and more, with social media, with, free press and so on, we have more demand on us as engineers, right, from the community. There are more expectations from us. Environment. Again, global warming is happening, we need to change. And we are the engineers. We are the people that have the power to change. So for future development, we need to look at where these three circles intersect, right? Economy, community, environment, which is a sustainability. We need to have a sustainable development. So within this context, my research group on the last 15, 20 years focus on accelerated bridge constructions and using recycled material. So in the US, we have the Federal Highway. So the Federal Highway is mainly the organization that's looking at the federal bridges. And right now they have a motto called get in, get out, and stay out. What does it mean? Get in, get out, that means we need to do our bridges just like this, overnight. The dream is to do your bridge overnight. This is really the dream. You go on, Saturday morning or Sunday evening and Monday morning it's done. So this is our goal. Get in, get out. Stay out. Stay out, that means we don't want to have major maintenance. We would like to minimize our maintenance. We would like to have bridges that last at least 50 years, 100 years, okay, with minimal maintenance. So the different techniques, as I mentioned, looking at moving a bridge as a technique, prefabricated superstructures. And if you are very familiar with the definitions, so I have here the drawing. So over here, you know, these are my girders. Okay, so anything girders and above this is my superstructures. Anything below this is my substructures. So I'm dividing my presentation to superstructures and then substructure. So I'm starting with the first technique to accelerate the bridge construction. Okay. Let me try it from outside. So the whole idea here is you don't want to demolish your bridge. So what we are going to do is you have a bridge that you need to replace. I'm going to construct a bridge aside of the bridge that I would like to demolish. Once the new bridge is completed, I'm going to demolish the old bridge and push the new bridge to replace the old one. Okay, so the bridge that we are looking at here now, they start the demolishing process, which take less than 24 hours. And at the same time, they are building the new bridge aside of the old one. This is the demolish process. Now you see the new bridge now is going on 10 hours. So you lose your traffic for 10 hours. It's done. So now you see now they are pushing the bridge, the new bridge, to replace the old one. Now you do, you know, the approaching slab and so on. So in total we are talking about, you know, less than 2 days. So 57 hours, almost 2 days. So this is the first one. So what they did over here is they would like actually also to have some widening. So they have a new abutment, okay, aside of the old abutment. So they have a new span now. So they have the new abutment, and then they have the two bridges, because it's two-way, so we have the two new bridges over here. And if you look over here, this span is different from this, but this is something related to the alignment of the bridge. So anyhow, they have the two new bridges that's built over here, and you have your traffic still use the old one. Okay, so you did not interrupt the traffic. Okay, and last year there is a new project in New York where actually even during demolishing, what they did, they have a shortcut from here going to the new bridge. So they use the new bridge here with temporary, you know, supports, and going back over here while they are demolishing. So literally they did not close the bridge except during the pushing the bridge back to its position, which is like 5 hours. And this was a major highway in New York. So anyhow, this is a pushing back pushing the new bridge now here. And let's move on to another bridge. So same idea. You see the new one now. So they have the new one ready. It's over here, there. And they're demolishing the old one. Now they started pushing the new bridge to replace the old one. And then, you know, you do the rest of your, you know, approaching slabs and so on. So it's really, we are very close to overnight construction of a bridge. Okay, so this was one technology. There is a similar one to this, but due to the time constraint, I'm going to present it. But there is a different technique also similar to this one. Okay. Now, what if you don't have the technology to do this one? So we start to come up with also new systems. So one of the systems that's really very recent on the US is what we call the deck bulb T-girder bridge. So on this one here, you have your deck coming as part of your girder. So the girder and deck come as a single unit. So if you look over here, this is my deck and this is a girder. So they're coming as a precast as a single unit. So what you do, you have all your girder, this is the longitudinal direction, so you have your all girder side by side, and then you have a little bit here of a joint that you are going to pour, and typically we are going to use ultra high performance for these joints. So you need 6 hours for the, to get the strength, and then you can open your bridge. Okay, so if you look, this is what you end up with. You have your, longitudinal girders, and then you have the red are longitudinal joint, and then you have transversal joint if you would like to have a continuity for your live loads. Okay, so this is looking from top how the joints looks like, the longitudinal joints. This is the steel. Well, as I mentioned, this is quite new. Okay, so we still struggle with some of the detailing, or we still, try to optimize the detailing over here. So this is how your girder, cross section for the girder would be provided to your construction site. You have the steel over here, and then you have either male-female connections or female-female connections, whatever. So you have the two girders, and you are going to bore this, as I mentioned, with the ultra-high performance concrete. And then we have over here different, we're looking at, as I mentioned, we still try to optimize the connections. So we have, to look at different steel detailing, how the connections looks like. Some tests, our colleagues at Lawrence Tech Institute, Dr. Nabil Grace, is tested some of these. So this is the connection here. So I tested as a beam. He would like to see if the rupture would happen on the concrete itself or the connection. So the connection is clear over here. This is another sort of connection. He also tested some slit test between the new concrete and the old concrete. He would like to see where is the shear are going to happen, whether just a surface between the two, the old and the new concrete, or within the concrete itself. Tension over here to see how is the tension resistance of the connections. Testing also in bending and check if, so this is the joint over here, you see the joint, and here is the load that he applied. And then he tested also a large scale beams. Okay, now the question is, what are you going to do with your diaphragms? So there are two schools over here. We try two different things. One of them is to not doing any diaphragms. The other thing is to have your diaphragm coming as part of your girders. Okay, once you have all the girders side by side, then you apply some lateral or transverse post tension. So we are post tension, unbonded post tension, everything, lateral post tension. Well, any new technology come also with some challenges. So the first challenge here, you need to be careful when you try to handle this one, because it's not symmetric, and it's you have a lot of instability here. So typically you need more than one crane to lift your huge girders now. Okay, the other one is stability. This girder over here, I think it's about 70 meters, so it's 215 feet, so it's about 70 meters long. So think about transportation and lateral torsional buckling that may be crucial during the moving of your girders. Okay, a third technology is what we call a full depth deck. This is the older one out of the three. So on the full depth deck panel, what happened is you have your girder. So we try to steal from the steel structures here. We would have post tension or pre-stress girders, and then we have the deck. So this is your full deck depth. We don't have two layers of deck. So it's just a single layer, full depth of your deck that's coming as a panels. and then you have some shear stud into the girders, and then you install, so this is a beam, you see here the shear studs, and then you install the full depth panels on top of these shear studs. Okay, now this is how it looks like. You install the panels. Okay, now we have different types of opening over here. So what are these openings? This is where you have your shear studs. So now I have my shear stud go through this box over here, and then you again using ultra high performance UHPC to fill this box. Okay, now the other openings that you need is the connection panel to panel. Okay, I have multiple panels over here, I need to connect them. So you have this weird shape over here to have the connection between the panels. Okay, and again we still try to optimize these connections. So here are different connections between the panels. Now the guy over here is boring the UHPC. So typically you need self-consolidated concrete with ultra high performance concrete. Okay, so this was my superstructure. Now I'm going to move down to the substructure, bridge columns, and I worked a lot with bridge columns. So if you are not really familiar with the seismic behavior of bridge columns, just would like to give you a 1 minute brief how a bridge column would behave under an earthquake or lateral loads. So over here we have, this is the axial load, and this is the lateral load representing your earthquake. So once you start pushing to my right here, what happened is you start to get some cracking, flexure cracking to the bottom, and then you keep progressing on the cracking, and then you start to get some bulging here on compression side, and then the bulging extend, and then you start to get bar rupture. Okay, so in other words, we design, and you get some bar buckling as well. In other words, we pre-design a location on a bridge column, what we call a plastic hinge, and all the deformations, the nonlinear deformation, would take place within this plastic hinge. Okay, if you have kids, sometimes you do you have a sandbox for your kids, right? So to dissipate their energy. We play with the earthquake the same game. We give the earthquake a sandbox over here, what we call a plastic hinge, to spend or dissipate the input seismic energy. Okay? So, we worked with kind of a technology of today and technology of the future. Okay? I'm sponsored most of the time by Missouri Department of Transportation, and Department of Transportation looking for some technology that they can apply tomorrow. Okay? So on this one over here, we are looking for a new technology that I think is really a fantastic one. So what we are doing here, this is the cross section of my bridge column. So a typical bridge column in the US would have probably a diameter of 1.5 meter. So the typical bridge column, this is the diameter. Okay. So what we do is we are going to change the cross section completely. What we have here, we have an outer tube, okay, the blue one here, which is fiber reinforced polymer, so it's kind of a plastics, if you like. And then on the inside, we have a steel pipe, okay, and then in between we'd have a sandwich of concrete. Okay, so the concrete thickness here out of, remember I'm talking about a diameter of 1.5 meter. The concrete thickness would be a 10 centimeter or less. Okay, so it's a huge saving in terms of material, huge saving in terms of weight of the bridge column. Okay, so this is how I'm just trying to do some samples here, how it looks like. So it's a donut cross section, steel, concrete, FRB. Okay. So the advantage, you can cut your weight and you cut your material by up to 75% in terms of concrete. So this is the FRB tube. This is my PhD student Omar is carrying the FRB tube. This is half scale. So a poor PhD student can carry the pipe himself. I don't have formwork. My two pipes act as a formwork. So I can't all the time, link it to the formwork. No formwork at all. Well, concrete cannot escape anywhere. If you remember my sandbox for the earthquake, we have some bulging, right? And we have some damage. After we testing some of these columns, you really will get the concrete as just sand. It's really crushed completely, but it's stay in place. It cannot go anywhere because you have from inside, you have a steel pipe, from outside you have FRB pipe. so where the concrete can escape. The other thing is we don't have any reinforcement bars. If you look to my cross sections here, where is the bars? We don't have any bars. We completely remove all the bars. We rely on the steel pipe. So think about the construction time. My student can do a conventional column, a conventional bridge column on the lab in 2 weeks. They are not professional, I understand this. But they took 2 weeks to do all the formwork, all the steel and so on. They did this one in 3 hours. Because it's easy. You have the 2 pipes fixed in place, have self-consolidated concrete or flowable concrete, bore between the 2 pipes, it's done. Okay? So, this is how you are going to provide your column, which most probably will be a precast column. This is how you are going to provide your columns. This is the FRB, the outer one, with the stop over here, and then I would have the steel extending beyond the FRB from the top and bottom. Why you are doing this? Now, this is I'm using it to connect the column to the surrounding elements, whether it's a footing or the girder. So if you would like, if you are in favor of cast in place, you would have your column provided as a precast, and then you have the formwork for your footing, insert the steel similar to this part over here, and the footing in your cage, and then bore the concrete for the footing. If you are a big fan for precast, everything precast, this is now my footing, okay, and I have the steel provided, the column, a precast column here, and I'm inserting the column into the recess that I already have on the footing. Okay, this is how it looks like. And then I have, you see here, there is a tolerance here. I'm filling this with high strength grout. Okay, again, think about the construction time. Just to give you the context, in Missouri, if you have a contract with the DOT, Department of Transportation, and you cut the construction time by 1 day, you get bonus, $10,000 from the Department of Transportation. So with each column here, we can cut, if I'm cutting the construction time for the column 5 days, it's $50,000 for the contractor. Then, everything looks nice on paper until you, take it to the test. So over here, this is our lab. The guys here, this is the chief engineer, bridge engineer of the state. So this is like the big guy for the design of bridges on Missouri. So he attended the test, and all the guys with the yellow hats here are state engineers that come to watch the test. The rest are my students and the technicians. So this is the bridge columns. It's almost half scale. Okay, so the height I think was close to 4 meters. And then we fixed the column to the lab footing over here, and then we apply some lateral force, backhand force to mimic the effect of an earthquake. Hopefully this video will work, hopefully. So this is how you do what we call a static cyclic test. Yeah, I'm just, reducing the time of the test. It's static, okay? I'm just accelerating the test. So you apply your lateral load backhand force to mimic the effect of an earthquake. Okay, once we have done with that, one of the question is what's happening to the steel pipe inside? This steel pipe would be under tension, which is great for steel yielding and with all the nice characteristics. What about compression side? So what we did, we have when you do what we call it, we have a camera, a video camera, one of these fancy small cameras that we inserted inside the steel pipe, so we can watch what's going on the steel pipe during the test. So over here, what we have over here, this is the side. I'm sorry, it's not clear because we just have the camera inside and it's vibrating with the test. But what we have here, this is the side. This is the vertical side of the pipe, okay? And we try to see what's going on with the pipe. So bear with me over here a second. Okay, it's over here. So this is the buckling. You see how the steel is buckled? Okay, but that's the good news is this was elastic buckling. So once you remove the loads, the steel comes back again to its vertical position. And we confirmed this when we're done with the test. We cut the FRB, we remove the concrete, and we look at the steel pipe, it's clean. And then, we would like to come up with a design equation so engineers can use our design here. So we came up, okay, one of the question is how much do I need to have an embedment length over here? So we came up with an equation for the embedment length. And we tried to play with this, who said our equation is correct? So what we did is we went to the lab again, having, what we think is not enough development length and another column with enough development length. So, as you know, if you don't have enough development length, we get, this rupture here on the footing. And when we have what we think is correct, this is the same steel pipe, the same, everything is the same except the embedment length. So it's a day and night here difference. And if we look to the moment versus lateral drift, this is just an indication if you design seismic, okay, this is the bad guy. What we have over here is we have a slip, and this is why, if you look over here, we don't have too much force, but we see a lot of deformations, which we call a benching. And this is the one with the enough development length. It's very fatty. So this is probably one of the few places where, we like fats. So whenever you have fat loops over here, it's much better than thin loops, because fat loops are an indication of they are dissipated high energy. That's an indication of you can resist higher seismic forces. Well, one of the things that we look at, okay, how we are going to do an inspection. By law in the US, you need to do an inspection every 2 years for every single bridge. Okay, so how we are going to do an inspection for the steel pipe. So I worked with my colleagues on electrical engineering department. They develop here what we call FSS. I don't have too much knowledge about it, but it's what they told me it is fast selective surface. So these are a 3D printed surface, and they have a certain shapes. And once they are under tension or compression, they start to deform. And this deformation, they can read with some cameras from outside. So the inspection would be a camera. The engineer would approach the bridge column with some camera that can penetrate through the FRB, through the concrete, would hit the steel, would read from this surface over here, and telling you how much the strain on my column. Okay, this is a hollow column. What about Saturday evening? Someone drunk, 120 kilometers an hour and hit the bridge column. What will happen? So we did some finite element analysis for a vehicle impact with the column. But first, we would like to look at the baseline. So we look at the formations with, this is a reinforced concrete. So all the black lines are rebar. So, we lost the concrete first, and you start to have rupture on the rebar. So you would expect to get significant damage if you have a vehicle impact. Now, when we move to the hollow core columns, it's more a global deformation for my column. So it dissipates the energy by global deformation rather than local damage. Now, next step, I would like to look at the future. What will happen to my bridge columns in service 20, 30 years, 50 years from now? So we just call Harry Potter here, try to understand what will happen. So we went to our environmental chamber. We have the columns, we put them on the environmental chamber, we load them, so we have an axial load applied to them, and we start to subject the columns to cycles representing the weather in Missouri. So we selected a very severe weather within 50 years, we compress this in 75 days. So we pick the very bad days and we just, brace them together. And then we run some compression tests, some tensile tests on the FRB. Well, with the new concept here, you can really get much better behavior than what we have right now. What about 10 years from now? Are we still going to continue use the same concept? I'm going to have a sandbox for my bridge so the bridge can destroy someplace? Because even with the new system, you still have damage, right? The FRB would rupture some at a certain time, okay? So what we have, our philosophy right now, what we call success, is you have a plastic hinge or sandbox and you are going to see some damage to the plastic hinges, and yeah, this is our success, okay? Well, look at the Greek. 100 years ago, or probably 1,000 years ago, this is their success. They have their columns, right? and the columns here, Greek is an active seismic region, right? And they have the columns here. I think this should be the true success, not ours, right? Ours is failure. So the true success is to have a bridge column that can sustain damage and perform in a certain way that avoid any damage under earthquake. So the key to the Greek columns is segmental construction. So what the Greek is doing is, if you look over here, they have what we call drums. So drum is just a single piece of stone, okay, and they have these stones on top of each other. So every time you see this line here, it's a piece of stone. They put them on top of each other, okay, no connection between these segments. And then they have a heavy weight on top of this. So what will happen? If you have an earthquake hit, what will happen is this would be your column, and then would just keep going back and forth. And you can continue as long as you did not really have a very high acceleration, ground acceleration to topple your column. You can continue forever. Okay. So I started by doing some literature review, around this concept. So what I found surprisingly, we use segmental construction a lot in the US, especially on the East Coast. So I was wondering, why we don't get this nice performance at the Greek guys. And what we found is the big mistake is reinforcement. Greek does not have reinforcement. We on the East Coast, when you use segmental construction, we have reinforcements. Okay, so what we do is we insert the segments on top of each other, and then we always try to mimic what we know, reinforced concrete. So we go back and we have a rebar, as over here, and we try to make these rebar, we grout them to have a reinforced concrete, more or less. But this is a Greek column section. Okay, what they do actually, they have some legs over here. If you see the two openings on the top, these two openings just like to have legs to avoid, to improve the friction. This one over here and this one over here. So we took one of these bridges, we took a quarter scale model of a bridge column here, and then we played the same game that I presented before, but now it's more advanced. So what I have over here, again, this is fiber reinforced polymer. This is a cross section of my column here. This is the fiber reinforced polymer, tube, concrete, no reinforcements or conventional reinforcement, steel pipe, okay, and then I have boss tension, unbonded boss tension that can be inserted inside the column. And then I have my column here. This is 4 segments. So this is the first segment, if you see this line here. Second segment, third and fourth. Okay, and then I boss tension all of them together. Okay, I don't have any what we call, it's just dry joint. I don't have any epoxy, I don't have anything between the joints, okay, at the joints. Just dry joints. And then boss tension, everything together. And I have my mass on the top of my column, which represent the bridge deck, and I put everything to our shaking table here, the yellow one over here. This is a unidirectional shaking table. Again, the video. Okay, we start always with a baseline, because this is a well-designed reinforced concrete column. So you see how much drift? It's still there, but you get drift, right? It's tilting. We don't have on the US, we don't have a standard who went to demolish a bridge column. However, the Japanese standard is if you have a Berman deformations more than 1%, that means the angle with the vertical is more than 1%, you need to demolish the bridge column. It's not economical to replace it, to repair it. Okay. So the bridge column that I presented has a lot of damage at the base and also has a lot of drift, so practically it needs to be replaced. Now this is a segmental one. Same earthquake. It's more flexible? Yes, it is. And then I did a visit at the Tokyo Institute of Technology in Japan, and they liked the idea, so we tested also some columns in Tokyo Institute of Technology. So what they have, Japanese are more greedy than we on the lab, so what they did is they said, okay, we are going to do the segments here on the bottom part, because this is where you expect to get more of the damage. And we use ultra high performance, okay, concrete. And my cross section, again, the one that I love is hollow sections, okay? So we use, but this is now is ultra high performance concrete. The thickness here of the cross section is 50 millimeter, and the height of the segment is 50 millimeter, okay? And we have 10 of those segments over here. Dry joints, post tension them together, and then the rest of the column would be conventional concrete. And then we did some testing over here. This is the chairman's coming, so. One of the things here is we try to increase the energy dissipation, okay, of my column. So on the same time, I don't want to get that damage. So what we did is I have, you know, in your conventional concrete, your sandbox, including yielding of the rebar. What if you remove this rebar to outside of the columns? Okay, it would yield, you get the damage, but it's fake because you can come after the earthquake and replace this, you know, yielded rebar. So what we did over here is we have the rebars outside of the columns, on the bottom of the columns. It's outside now, okay? And now we discuss with the architect how we are going to, you know, make it looks good and so on, but it's outside. So it's like the fuse in your, you know, old days when you have a fuse in your building, on your, you know, on your apartment, and then when you get, you know, the higher voltage, you know, you cut the wire over here. We use the same concept. Okay, I'm not going to skip much of these details, but this is how a well designed. This is designed according to our best practice right now. Okay, so this is what you get. You get rupture on the rebar, you get damage, you know, at the plastic hinge, and you get the tilt over here. These are my babies. The one with energy dissipators, the other one with no energy dissipators, brand new after testing. Now we're looking at how much is the residual displacement after you have done with the test. So we look at, okay, how much is the residual displacement? So the one that you literally cannot see on the bottom over here, all of them are the segmental ones. The one that's outstanding, which is bad here, is the reinforced concrete column. You get too much deformations after you're done with your earthquake. And then we did some, you know, finite element models. We proposed some design procedure. And with this, I would conclude my talk here. Accelerated ABC is accelerating bridge construction is not dream anymore. You can do a bridge overnight. We are working to cut this, but right now you can do it, you know, 24 hours, you can do something. New challenge has appeared when we start doing, you know, the ABC. One of the things now, when we try to post the columns, what about the loading case? You know, the IBC or whatever the building code that you use doesn't have a load combinations when you start pushing the column, the bridge to the new position, right? When you do all these connections, what sort of, you know, testing that you are going to do? What about inspection? So you have opportunities, but it comes with challenge. Prefabrication is really crucial for accelerating bridge construction. And at the end, I would like to thank my former students and my current students and all my sponsors. Thank you so much. Thank you.
So again, thank you so much. We have a few minutes for questions. If anybody would like to ask a question, please.
Thank you very much for your distinguished presentation. My question is, the column that we saw before is hollow tube filled with steel pipes and FRP shell. So my question is, if the problem is the weight of the column,
Can we replace this type of columns by composite steel columns filled with lightweight FLA concrete instead of this?
Well, remember I cut 75% of the weight of the column because the steel pipe is hollow, right? So even if you replace the 1.5 diameter column with a lightweight, how much you are going to save in the weight? 25%?
You mean the weight of the total weight of the column?
Yeah.
I replace the hollow section
Okay.
with lightweight FLA, not normal concrete.
Okay.
Lightweight.
Yeah, you can, yeah, for sure.
Can we do this?
Yeah, I think so. Because concrete, as I mentioned, concrete is confined between the two pipes. So we can get advantage. Actually, one of the columns here we have by mistake. It was not design. But the precaster, the ready mix provide us with very low strengths. And we're not sure whether to test or not. But we did the test of the columns, and the result was really fantastic. Thank you.
Just I need to ask about this column. You said we will use the post-tension situation if we have 4 poles, something for this column. Which technology we can use it for connection from down to top?
Now, I worked with the post-tension before. We should have end and something fixed in the end. You can push it in the second area or second direction. But in this case, how we can do it if the footing down and I will put column over and over, I will put post tension. Thank you.
Thank you. So these columns, we anchor the dead end for your anchorage is on the footing. So even for this one, we have the anchorage in the footing. This is for the new construction.
Okay, that's the cables will be done already from down and go up. Then we will post tension from the top.
You post tension for the girder with the girder, so you would post tension your column with the girder. Yes. And actually, if you are interested, you can look at Washington State, DOT, Department of Transportation. They already have a bridge using this concept. But it's not segmental, it's just at one segment, and they post tension everything together.
Okay, thank you.
Thank you.
No, I think it is not allowed in the bridges to use lightweight concrete at all.
What?
It is not allowed in the United States of America to use lightweight in bridges.
Okay.
You cannot do it at all.
Well, many
it's forbidden.
Many of the things that I'm presenting here are forbidden by the code. But remember, we are the one that makes the code. Many times you don't really allow the code because you don't have the knowledge, or you don't have really a very limited database. Here we try to push the envelope. So if you try to push the envelope, like I have a colleague working with the mechanical anchorage for the rebar, also for accelerated bridge construction. By the code, you cannot do this. You cannot have the mechanical anchorage at the plastic hinge. But if you would like to push the envelope, you need to try new things, like unbonded post tension. Like the British code doesn't allow unbonded post tension at all in bridges as well. But again, if you would like to push the envelope, you need to take the risk. Yeah, please.
Thank you for your very interesting lectures. I would like to know what is the maximum span you are using for the technology that you don't use diaphragm.
Well, okay. Remember, the big bulb is still kind of like right now they try to optimize the parameters, but right now they have about 100 feet. But 100 feet, the span is 100 feet. But I'm not sure about the diaphragm. I'm not sure I can look for whether the 100 feet, sorry, not 100 feet, 100 meters, it's 300 feet. So they have a 300 feet dig bulb. But I'm not sure about whether they have a diaphragm on this particular bridge or not. I can look and tell you.
The other question about the column.
Yeah.
We are using the FRP. This is for confining, and we'll take the confining.
Yeah.
But it is expensive. Is it?
Okay. Again, I'm working with I'm working with a very practically oriented engineer. The Department of Transportation are really looking to save every single penny. You see at the beginning of my presentation, they have a 50% shortfall on their budgets, and this is more or less an average in the US. So what we tried is we looked at two different types of FRP. One of them is the one that used pharmaceutical companies. This one is very expensive, I agree. But the second one, Missouri is not high seismic zone. So we don't need to have a huge confinement. So what we did is, I don't know if you have this system over here, but there is glass fiber that's used as a piping for drainage system and bridges. Like if you have rains and so on, you collect all this in a pipes, which is really a very thin pipes. It's very cheap. They already use it as a drainage for the bridges. So some of my columns actually tested with these pipes, which is not for structure. But again, we experiment with all these materials. So one of the things that we tried as well is PVC. High strength PVC. Can we use PVC instead of this one? Can we use corrugated sheets, pipes, instead of the outer side? But this is still work in progress. We try to optimize the cost versus performance.
Possible?
Yeah. Okay, thank you so much.
Thank you so much. About the design of self-healing composites. Professor Basso comes from the Institute of Ad-Dar Institute of Technology in Kundana, Bangalore. He is a professor there, and his past education, his first degree, BS in Engineering from Catholic University in California, and then MS Engineering from the University of California at Los Angeles, and the third PhD was from Eurotechnica. He has a research interest in renewable energy, materials, FDT, CAD, CAM, and robotics. Professor Basso, please take the chair.
Assalamu alaikum. Thank you for being here to listen to my lecture. I am very pleased and honored to be here today as a speaker at your conference. So I am basically a materials and mechanical engineer, but mechanical engineers like to include everything else in their field. And civil engineering, now we would like to include that also, but so far it is separate in our curriculum. But there are many common courses like composites, strength of materials, hydraulics, and structures, and finite elements, and so on and so on. But there are some differences because laboratory is different. Anyway, I will not divert the topic. So I am going to talk about the design of self-healing composites. So what is this self-healing composite? This slide will show you what the basic structure or microstructure of such a material is today. We have a healing agent which is embedded in the matrix. So what happens is when a crack forms in the material, these capsules break and the healing material comes out and goes to the crack by means of, as you may know, Darcy's law, that is a pressure difference, pressure gradient. It automatically finds its way, like water finds its own level from high to low. This material will heal itself by means of the flow of the embedded agent. So this can be super glue or some other compound which hardens in contact with the catalyst which is in the matrix. So the crack is closed by means of this bonding, and then it can also work at micro level. Now, what are the materials that are used? We have this DCPD, dichlopentadiene, microcapsule which is urea, which can be as small as 166 microns, chemical catalyst, flexibilizer, polymer matrix, and fiber reinforced, carbon fiber or fiberglass or whatever you have. We can also have voltage induced action, which is voltage difference J causes a flow electrohydrodynamic gradient. And then the density, particle density increases at the crack and coagulates, as you can see in the right hand side. So this is a magnification of what's happening. We have the microcapsules and polymerization at the cracks. So the self-healing materials, I'll give a little bit of the history of this thing. It started basically at the start of this 2000 era. This was originally a lot of research done by the American Army, US Army, after they went into the Middle East, where they found that their armor was not up to the mark. A lot of casualties were happening, so they decided to look into this self-healing armor, the armor which could be repaired. And nowadays we talk about sustainability and all that. So it is beneficial from the point of view of the environment also, because you don't want to throw away a bridge which breaks. See, a lot of energy goes into making the bridge, a lot of water, a lot of electrical energy, a lot of fuel is used for the trucks to bring the concrete, water is used, and so on and so forth. So if the concrete can repair itself, we have a saving in the carbon footprint. I think many of you have heard what is carbon footprint. Anyway, now this is a buzzword in terms of sustainability. So these materials are sustainable. So they can, you don't have to throw it away and cause, rubbish to be thrown in the sea or in the landfill. It repairs and you can use it again for a certain amount of time. So there are two mechanisms, which is autonomous and non-autonomous. In autonomous, you have a automatic self-healing. And in non-autonomous, it is you need to activate it somehow by external trigger, like heat or light. So for example, plastic, which breaks, you can repair it by heating it. Melt it and again heat it. So some plastics can be done this way, like polyvinyl, PVC and all that. But others, like your keyboard, they cannot break. They cannot be repaired like that. So this is one of the reasons why the rubbish people who collect the keyboard, they don't give you much money for that, because it cannot be recycled. It is throw it. So this is the two types. So self-healing material, when you have a damage inflicted, crack occurs is in part A, then goes on to part B, which is a triggering of a mobile phase, and then you have transport going to the crack from the mending reaction. This goes to the interconnection of the cracks. So this capsule breaks and the fluid will flow and go to the crack, which is a lower concentration. So you have a concentration gradient or pressure gradient. If you want to think of hydraulics, you have a pressure gradient. You will go from high pressure to low pressure. The fluid will flow automatically. It is sort of some intelligence is there. So once fluid hardens, then it stops automatically. So there is no need to have any control after this. So now the mechanism for the design is either use a capsule or a tube, hollow tube or microcapsule. We have what is called a monomer, which is some kind of a polymer. Not a monomer is different from polymer. When you heat it, it becomes polymer. So monomer is encapsulated and enters the crack where it forms a mend of the crack. And in a hollow tube, it's like a fiber or capillary. We have the other kind of geometry. This is basically cylinder and sphere. So these are the important characteristics, and the main thing is catalyst. If you use it, it must quickly dissolve and react, and should not prevent the crack from going further. So those of you who are interested in the equations, this is a sort of diffusion type equation which is to be solved for these kind of problems. Usually they do it for the thermal equations, but it can also be done for the concentration gradients, which is, you can also add pressure terms, but I don't think anybody's done this. The pressure terms have to be added also if you are thinking of hydraulic gradients. And the basic solutions for these are the diffusion equation solutions, which are called the error functions. These are closed form equations, closed form functions. The cylinder has the exponential integral or Bessel function, and the sphere has what is called a spherical error function. So the solutions are well known. They are given in classic textbooks like Carr's law, Jaeger, and Patterson gave the solutions in 1952 for the different geometries. Basically, this is a moving boundary problem. We have a non-linear problem because the boundary is moving. So the equation is different from both sides of this phase boundary. The properties of the material are also different. And to solve this kind of equation is rather difficult because it is not possible in a closed form. You have to use numerical methods. Very difficult to solve, and only few exact solutions known. One of the first was given by Stefan in 1890, and the reason was when the Tsar of Russia gave up Alaska to the Americans, he wanted to calculate the area of the ice. Now the ice melts and freezes depending on the season, and the melting of the ice was a problem which was solved by Stefan. How much the ice moves over the course of 1 year, you see. It involves maybe thousands of square miles, because the Alaska was part of Russia earlier, Siberia, it was part of, so they sold it to the Americans. And the Tsar wanted to know this, so he gave it problem to Stefan, and Stefan's problem is a well-known problem, which is there in many textbooks. Now this diagram here shows what is happening when you have the change from liquid solid. In the vertical line shows the phase boundary, and the tangents are shown by the red lines. So the equation which I showed earlier involves the gradients at the boundary. The dc dx or dt dx are the gradients. So along on either side of the interface, liquid solid, we have these diffusion equations. So as I mentioned, the pressure term is not included, but you can add it. And these are the classical solutions for the sphere. We have the non-dimensional parameters on the x-axis and y-axis. You see for different combination how it moves. Now supposing we change the diffusivities for the matrix and the liquid which is doing the repair. So based on the ratio of the diffusivities, you have the velocity of the flow. It's basically linear type of relation. So this is one way we can control the design of this self-healing by varying the diffusivities, which is, you can get it from your common sense also, but this is equations. So the more permeable the matrix is, the faster it will move. This is what it is saying. The more porosity you have in your material, the faster this liquid will come out and go. So this has been verified by calculation. And there are now, since it was started by research, started by military, it has now gone into the consumer field. We have slowly coming out in the form of self-healing paint, then self-healing construction materials, self-healing I'll show you some of the examples. So here, another kind of design where you have a interpenetrating vascular network, that is like your capillaries in a tissue. So the rationale for this design is to copy nature, how nature heals itself, whether it is a plant or animal or most living beings, they will have some kind of repair mechanism. This is how it works. So they have the interpenetrating capillary network, and this is the mechanism how the healing occurs. And in simulation we use two types of materials, organic inks with a viscoelastic behavior but different time, temperature, phase change properties. So if those are interested, you can see the chemical compositions of these things. So this is another one here by means of electrospinning encapsulation. We have two tubes, a spinneret with two coaxial capillaries. The viscous fluids are fed, and the electrohydrodynamic forces are used to stretch the fluid interface to form coaxial fibers. So you have coaxial fibers which can be filled, the inner space can be filled with the healing liquid. So how this healing occurs after rupture, this is one of the by means of reaction and forming cross-linked material. So the crack, wherever it is, this liquid will come out and form a polymerized cross-linked compound. So this is another mechanism. This after your thermal and the other electro mechanisms, we have the polymerization, which is used for self-healing. So polymerization is some of the micrographs are there showing how this is basically glue which is hardening. It's some kind of super glue or whatever you can call. So this cross-linking is how this super glue hardens. So here is a better description. You have the crack in a, say, panel with hollow channels, and when the crack occurs, the liquid flows into the other hollow channels. It goes from the parallel channel without fluid, goes and fills it up and forms a bond. So it hardens and gives a strength to the material. And of course, you will not get 100% strength, maybe 80%, 70%, but it is okay. Instead of throwing away the material, you can keep on using it, you see. This is the idea. So here is a simulation of surface. Surface has been cracked, scratched by a tool, and how the paint gets healed. You see the bottom graph shows the profile. After time, how it heals. So here we have also a smartphone cover, self-healing smartphone. This is already being used by LG. LG is a well-known mobile phone. I think many people have this LG also. Samsung has not got it, maybe LG has got it. So smart material which heals itself. So the scratch will disappear before your eyes, like you have in this case. You see how it is. See, the profile changes. This is what then you see if your car is scratched by some hooligans, or you leave it in a parking lot and someone scratches it, doesn't like you, it will repair itself. This is you don't have to spend so much money to paint it out. If your car is scratched, you will have to pay a lot of money the car repair shop charges you a lot. So this coating, which maybe you pay a little more to have the coating put, the scratchings will go away after this healing sort of surface graffiti and all what people like to write, or just scratch your car. They can get rid of that. And then the other application is in concrete, self-healing cement, self-healing concrete. This is another area which is being developed now, which is they use some kind of a reaction involving bacteria. So the bacteria involves precipitation of carbonates. It's very interesting. The carbonate is formed by the bacterial reaction. So this particular bacteria, Megatherium subtilis, is used to react with urea and form the calcium carbonate deposits. And another application in the epoxy with fibers in aircraft. So self-healing aircraft, when you have a hole or a crack, the resin leaks out and seals the brake, returns to 80 to 90% storage. Earlier, what they would do during maintenance is when they find a crack, they would drill a hole at the start of the crack. That reduces the stress concentration, so the crack doesn't spread further. And this is used to be written in the maintenance records. So one interesting case was when one of the British aircraft disappeared in the 1950s. It had been repaired like this. So when they recovered the fuselage, it was in the Bermuda Seas, they found that this started at that place where they had drilled the hole. So the areas of further work are in the, say, roofing sheets, car bumpers, car parts. It's very expensive to get your car repaired. Just plastic, but the car companies charge a lot for these replacements. To replace a car bumper, it will cost you quite a bit. So many people just leave it like that. Earthquake buildings, earthquake-prone structures, beams and columns, aircraft components, and concretes and cements. So these are just a few of the applications. There are many more. It's an area of active work, active research, and many companies are still working on this. They don't like to disclose until they file international patent and then they put it in the market. But it's a very, very fast developing field and involves many technologies, many interdisciplinary technologies. So I thank you very much, and I hope that this has been of some interest to you, and if there are any questions, I can answer them.
Thank you, Professor Basso. I think we will have all the questions at the end of the four speakers. Thank you so much, Professor Basso, and we will go forward now with our second speaker, Engineer Shahad Muhammad Ramman. Mr. Engineer Ramman will talk to us about the recycling destructive concrete in building construction. Engineer Ramman is working with the Zarqa University in the engineering faculty of civil engineering department. He is an assistant professor, then is Dr. Shahad Ramman. He is an assistant professor in civil engineering structure. He holds a PhD degree from the Jordan University. He worked in several places, including University of Isra and Zaytuni and Al-Azraq University. His research interest is in reinforced concrete structure design, precast concrete, steel structure, earthwork engineering, and construction materials. Thank you, Dr. Ramman, and I leave the floor for you.
نحطه بس على الأرض هون تحت. شكرا. بسم الله الرحمن الرحيم. بداية أود أن أعبر عن عميق شكري لكم أيها السادة العلماء والباحثين والمهندسين، حضوركم ومشاركتكم لنا في هذا المؤتمر الدولي، آملا أن ينال بحثي هذا والموسوم بإعادة تدوير الخرسانة المدمرة في إعادة البناء اهتمامكم وعنايتكم. Recycling is a part of environmental consideration has become a common feature in the construction industry, construction and demolition. Debris is the waste material that results from the construction, renovation or demolition of any structure, including buildings, roads and bridges. Typical waste material has only recently gained attention as concerns about its environmental impact have developed. One of the things builders, developers, and contractors must consider during construction, renovation, or demolition is where to put all the debris. يعني المقصود بالبحث كله إنه إحنا بنعمل عملية إعادة تدوير للخرسانة المدمرة في صناعة خرسانة جديدة. حين الخرسانة الجديدة اللي رايحين نصنعها إحنا مش راح تكون بنفس المواصفات للخرسانة التقليدية اللي إحنا كنا بنعرفها. لاعتبارات عدة راح نستعرضها في هذا البحث. هذا منظر عن الدمار اللي حصل في غزة بعد الحرب الإسرائيلية، العدوان الإسرائيلي على غزة في 2006. Recycling of concrete debris can make a contribution to reduce the total environmental impact of the building sector due to use of the recycled aggregate in construction, energy and cost of transportation, natural resources and excavation is significantly saved. This in turn directly reduces the impact of the waste material and pollution on environment. This study will investigate the best ways to repair and reuse buildings, paying particular attention to the reconstructed damaged buildings. من ضمن الأخطار اللي ممكن تحدث نتيجة عملية الهدم اللي بتتم للمباني القديمة في استعادتها في مباني جديدة اللي هو البوليوشن تبع الجو، تلوث الجو، وهذا مشكلة كبيرة جدا يعاني منها المهندسين والمختصين. Recycling of waste concrete is done to reuse the concrete rubble as aggregate, gravel and fine. The recycled aggregates have less crushing strength, impact resistance, specific gravity and has more absorption value as compared to fresh aggregate. بالمعتبر والمتوقع انه راح يكون السترينث تبع هذه الخرسانه المستحدثه او المدوره من الخرسانه المحطمه بالاكيد راح يكون اقل تحملا من الخرسانه التقليديه العاديه. لو اطلعنا على هذا المنظر بوضح لنا اللي هي الكونكريت ديبريس فروم لاند فيلز، هاي من المناطق اللي بصير فيها الدمار. بنحاول قدر الامكان انه نستخلص مواد الخرسانة المكسرة والمحطمة لإعادة تدريجها من جديد وإعادة صناعة الخرسانة من جديد. الآن في عندي سايكل بدنا نمر فيه من خلال إعادة التدوير. أول خطوة اللي هي عملية الإزالة أو التحطيم demolition، الكونكريت رابل، بعدين الهاي كواليتي aggregate manufacturing plant, recycling aggregate, ready mix, then reconstruction of the new building. Using recycled material as a gravel reduces the need for gravel mining. There are also economic benefits. يعني الآن زي ما أنتم عارفين إحنا الآن لما نستخدم الخرسانة المحطمة اللي already هي موجودة عندنا في الموقع بنوفر على حالنا عملية ما يسمى بالتكسير والتحجير ودفع تكاليف باهظة، لأنه المادة الرو ماتيريال ببلاش، إنما هي محطمة ومكسرة والمطلوب منا إزالتها حتى نزيلها لمواقع خارج المدينة. تكلفة عملية ترانسبورتيشن، عملية نقل وإيجاد فراغات واسعة جدا لهذا المادة، فإحنا بنستفيد منها إن نفس المادة الخام هاي بناخذها وبنكسرها وبنعملها ريسايزنج وإعادة تدوير كركام، ومن ثم بنقوم زي ما تحدثنا عن إضافة الإسمنت وإعادة صناعتها. The mix needs slightly higher quantity of cement or using admixture to reduce the water requirement. Experimental investigation project design. زي ما حكينا العملية كلها تلخص بالخطوات التالية. الخطوة الأولى نحصل على الكونكريت دبريس اللي هو الحطام تبع الكونكريت، كولكشن، نعمل له كراشنج، بعدين جريدنج، بعدين ميكسينج، كيورينج، تيستينج اند ايفالويشن. الايفالويشن من خلال الاختبارات اللي احنا بنعملها، واهم اختبار بهمنا اللي هي عملية قياس قوة تحمل الخرسانة. هذا الملخص اللي حكيناه، انه نجيب مادة الدبريس هاي الحطام تبع الكونكريت، نعمل له كراشنج، جريدنج، ميكسينج، وبعدين بنجيب هذا المادة المحطمة بنضيف عليها الماء والإسمنت كما بنعمل في الخلطة الخرسانية العادية، وبنخضعها لفحوصات في مراحل الصناعة. كمادة الفريش كونكريت بنخضعها لفحصين، السلامب والبنتريشن تيست، لأنه هذول أهم فحصين بقيس الامتصاص والهبوط. والفحص الثالث بكون عملية الكومبريشن تيست بعد ما نعمل كيورينج للخرسانة من خلال عمل مكعبات واسطوانات. زي ما انتم عارفين هذه الخرسانة كسرها بعد 7 أيام، 14 يوم، 21 و28. إذا نجحت هاي المواد فمعناته احنا حصلنا على خرسانة جديدة بمواصفات مقبولة. إذا فشلت في الاختبار بنرجع بنعمل إعادة تصميم من جديد، ونرجع على الخطوة الأولى اللي حكينا عنها في البداية اللي هي عملية إعادة التدوير. يعني بنرجع هون إذا كان فيلد بنرجع على عملية الميكسينج من جديد، وبنمشي نفس الخطوات السابقة. اوبريشن اند تيستنج بروسيجرز. طبعا في الخطوات اللي احنا بنعملها مشان الحصول على هذه الخرسانة الجديدة بنعمل سيف اناليسيز، نعمل بنتريشن تيست زي ما حكينا، سلامب وكومبريشن. الآن عملية التقييم. The compressive strength of mortar is sometimes used as principal criterion for selecting mortar type, since compressive strength is relatively easy to measure and it's commonly relates to some other properties such as tensile strength. طبعا tensile strength زي ما انتم عارفين ما بنقدر نحصل عليه للكونكريت بالسهولة، لكن ممكن نعمل للمورتر عينات ونحسبها على الشد تنشن ونقارنها مع المواصفات. الآن results and discussions. بدنا نلاحظ نسبة الخلط اللي رايحين نحصل عليها أو نعملها مشان صناعة الخرسانة وصناعة المورتر. For compression and penetration test نأخذ 24% سمنت، 11% ووتر، 65% crushed concrete من الدبريس اللي حكينا عنه. For the slump test 11% سمنت، 60% ووتر، 29% crushed concrete. The amount of water and cement are plotted to find the effect of the mixed proportion in the cementitious material. These values were obtained by using ratio and proportion. زي ما حكينا في الكونكريت بناخذ 1 part cement، 2 part sand، 3 parts 20 ملم gravel، وهاي الكميات في المتر المكعب من الخرسانة. بينما للمورتر بناخذ 1 part cement و5 أجزاء في المقابل من الرمل. التحليل المنخلي نستخدم فيه منخلين أساسيين، اللي هو منخل رقم 4 لازم نسبة المار فيه تكون حوالي 100%، ومنخل 200 نسبة المار فيه 10%. الآن في اختباراتنا للبنتريشن تيست وجدنا إنه the average difference of the penetration of the standard mix is 9% higher than the average of the concrete debris mix. عندنا فحوصات السلامب اللي معمولة للمورتر والكونكريت بتعطينا فكرة إنه السلامب ستاندرد ميكس 18 ميلي، لكن للخرسانة المصنعة من الخرسانة المدمرة 19 ميلي which is very close. يعني ما في عندنا مشكلة في السلامب، لكن لو أجينا للمورتر المورتر بكون السلامب فيه من 12.5 إلى 20 ملم which means بكون أكثر نوعا ما. في اختباراتنا للكومبريشن تيست زي ما أنتم ملاحظين لو جينا للستاندرد كونكريت، الستاندرد كونكريت ملاحظين بكون أعلى من الدبريست كونكريت أو الريسايكلد كونكريت. بعدين ايش بصير عندنا تقريبا بتقاربن وبيزيدن مع بعض تقريبا لينيرلي. بعدين شو هنا الخرسانة الكلاسيكية العادية بتزيد بشكل واضح عن الخرسانة بعد 28 يوم. لو أخذنا الفرق بين هذول الرقمين فبنلاحظ حوالي 17% الديفرنس بينهم، مما يعني إنه هاي الخرسانة اللي استطعنا نتخلص من العوارض اللي فيها والمشاكل من إعادة تدويرها، هاي بنتخلص أول شيء من المنطقة، من فض المنطقة اللي فيها هذا الدمار بأقل التكاليف، بدل ما عملية النقل والإعادة الاستخدام نستخدمها بطريقة إنه نوفر فلوس وفي المقابل نحصل على خرسانة تحملها يعني within الكونكريت العادي. في الخلاصة recycling destructive concrete in building reconstruction is the preferred method of management due to the proximity of limestone mines and distance زي ما حكينا of recycling facility or landfill. النقطة الأولى بنحكي عنها اللي هي في الخلاصة the proportions of the crushed concrete debris affects cement and water in a manner that it absorbs most of water in the mix for lubrication. احنا بنعرف في الخرسانة العادية المية موجودة للإماهة للإسمنت، يعني عملية الهيدريشن للإسمنت بيكون هذا في المية، لكن في حالة الخرسانة المدمرة واللي بنعيد تصنيعها في جزء من الماء بروح لعملية التشحيم، لأنه هاي الخرسانة بتكون خشنة جدا وتحتاج إلى عملية تخفيف من الاحتكاك حتى نقدر نحصل على الوركابيليتي المناسبة. The concrete debris mixture obtained the high slump and low compressive strength as it is 7th day of curing في اليوم السابع. The amount of water in the mixture affects the consistency of the mortar mixture. The concrete debris mix with 1:3 ratio of the cement to crushed concrete with considerable slump and penetration has an mobility as the standard mortar mix of the same cement to sand ratio. يعني المقصود في هذا الفقرة إنه أنا لو استخدمت في صناعة الخرسانة الجديدة 1:3 بين الإسمنت وبين الخرسانة أو الركام المكسر من الخرسانة بحصل على سلامب وبنتريشن قريبة جدا من الخرسانة العادية، مع الأخذ في الاعتبار زي ما حكينا اللوبريكيشن اللي هي عملية التشحيم أو ما يسمى بالتخفيف الاحتكاك. Finally, it is possible to reconstruct the buildings from their debris-destructed concrete. It is reality to rebuild the structures again. يعني ممكن نعيد صناعة الخرسانة المحطمة واستخدامها مرة ثانية في إعادة إنشاء مباني جديدة ومواصفات جدا مقبولة، ما بنقدر نقول إنها أحسن لكن بتكون مقبولة وأكسبتابل للمهندسين. وشكرا.
نشكر الدكتور شحادة النام على المعلومات القيمة اللي أعطانا إياها، وراح نفتح باب الحوار ونخلص الثلاث سبيكر.
ماشي، شكرا.
الآن لكم الدكتور أيوب أبودية والدكتور زيدون سالم والمهندسة آلاء خضر يحكونا اليوم عن الجرين لو كوست هاوسنج يونتس. والدكتور أيوب من جامعة الزيتونة وهيد اوف ذا تشارتر كونسلتنت اون جرين بيلدينجز وهيز مين ريسيرش از جرين بيلدينجز اند انرجي افيشنت ديزاين. تفضل.
شكرا مهندس رجاء، الله يعطيكم العافية جميعا. بداية هذا المشروع يخص سكن معقول التكلفة وسكن أخضر للاجئين. أنا ما بحب أستخدم كلمة لاجئين، للضيوف السوريين في الأردن في منطقة الزعتري. انعمل في كليتين، كلية العمارة في جامعة الزيتونة وكلية الهندسة المدنية والبنية التحتية، اللي اشتغلوا فيه أنا والدكتور زيدون والدكتور لؤي دبور والدكتور مشرق حمدي، نسيت حدا؟ والطالبة طالبة العمارة عندنا على وشك التخرج الآنسة آلاء، إن شاء الله مهندسة آلاء. فكرة البناء الأخضر من هون لما يفتحوا لنا I would like to apologize for those who don't speak Arabic. I think the audience is the majority are Arab speakers, so please allow me to speak in Arabic, considering there is a translation. Thank you very much. وبناء عليه مشروعنا عبارة عن مجموعات سكنية للضيوف السوريين. تصميمها مميز من حيث انه درسنا البناء الحراري تبعها، الطبيعة الحرارية تبعها، الراحة الحرارية تبعها، درجات الحرارة اللي راح تشوفوا بالتفصيل من داخلها، بحيث تحقق الراحة الحرارية للسكان، وفي نفس الوقت شكلها مناسب للبناء الصحراوي، مقتبس من الصحراء السورية بالمناسبة. البناء اللي في قبب انتم بتعرفوه يعني الا تكونوا شفتوا صوره، مبني من الطين. اضفنا في الحقيقه قش، زي ما انتم عارفين الادوبه هو بناء مبني من الطين، خلطناه بايدينا من القش، وايضا عملنا اضافات على ريسايكل ماتيريال من اكياس النايلون تبع الخدمات اللي بتيجي سواء الرز او الطحين حتى نعيد استخدامها. وحطينا مادة عازلة في داخل الجدران، بمعنى انه الجدار الخارجي كان من طبقتين من الطوب، من الداخل عملنا ريسايكلينج لمواد العزل الحراري الموجودة في المناطق الزراعية، سواء كانت في الازرق او كانت في الاغوار. بتعرفوا البوكس البوليسترين هاي كفاءتها عالية في العزل الحراري، ولكن بعد ما يخلصوا منها بتتكسر وبترتمي وبسحبها الهواء زي البلاستيك، فعندنا استخدامها في داخل هاي الجدران. واخيرا فتح الباوربوينت. انا دائما بحضر حالي لمحاضرات احتياطا حتى لو ما فتح، فانا كان عندي ماده اكمل، فانا بدي احاول احكي 10 دقائق. نعم خلص، شكرا. بحاول احكي 10 دقائق، صرت حاكي 3 4 وخلي الاء تكمل. اذا هاي صوره من معين. لاحظوا كيف الابنيه القديمه كان تصميمها جميل، كان تصميمها لونها حلو، من الابنيه المحليه، مثل هذا الكهف اللي موجود بالسلط قديم. يعني اجدادنا كانوا يعرفوا كيف يبنوا ابنيه مريحه حراريا من مواد محليه. للاسف لغايه اليوم احنا مش عارفين ندبر حالنا، حتى بنحاول نقنع الناس انه في الابنيه اللي بتطلع في عمان ما تتركوا فراغ هوائي في الجدران، لانه الفراغ الهوائي كفاءته متدنيه، يكون في ماده لها كفاءه عاليه في العزل الحراري. فكره الابنيه المتلاصقه للجبال ايضا كانت معروفه. لاحظوا هاي البيوت هي بتستخدم الجيوثيرمال انرجي تبع الصخر، تبع الماده الطبيعيه الموجوده، ومستقرة حراريا على مدار الفصول. ولذلك في أبنية الآن تقام بأمريكا على سبيل المثال في داخل الكهوف وداخل المغر، لأنه درجة الحرارة مستقرة. وهذا الحكي مش جديد علينا، كلكم بتعرفوا البتراء، الأنباط بنوا البتراء بناء على هاي الفكرة. وبالمناسبة في عصر بناء البتراء كان في القرن السابع قبل الميلاد والسادس والخامس، بهذيك الفترة كانت برودة مناخية. إذا بتفتحوا على الكلايمت تشينج بتشوفوا أنه كانت في فترة برودة مناخية، ولذلك استفادوا من الطاقة الدفينة الموجودة في الصخر للعيش فيها. إذا إحنا بدنا نعيد الاستفادة من هاي الفكرة. هذا منظر مجسم عام للمشروع، تفصيلاته المعمارية رح تسمعوا عنه بعد قليل. هاي صورة أيضا من بلدة الإسماكية، بيت مهدوم في محافظة الكرك. لاحظوا المقطع في السقف، مقطع سميك من الطين والقش المتوافر محليا، لونه أصفر. وانتبهوا، اللون الأصفر الصحراوي والطين البني ألوان مناسبة جدا لانعكاس الحرارة وخفض انبعاث الحرارة في فصل الشتاء، بمعنى فقدان الحرارة بفصل الشتاء بيكون أقل، بنفس الوقت عكس أشعة الشمس عالي. انتبهوا، هاي المواد الطينية عليها طبقة مايكروسكوبية من النباتات، يعني إذا بتحطوا إيدكم عليها من فوق بتلاقوا في قش بيطلع عليها في فصل الصيف وفصل الربيع. هذا بنشف، هذا له دورين مهمين. أولا بيعمل ظل في فصل الصيف ولو قليل. ثانيا بخفف من سرعة الرياح الملامسة لسطح البناء، وبالتالي بتزيد من كفاءته الحرارية. وإذا بتفتحوا على الكود الأردنية، وأنا اشتغلت على الكود الأردنية، إذا بتفتحوا على الكود الأردنية بتجدوا الآر فاليو عالية إذا كان منطقة سرعة رياح متدنية. إذا له فوائد كثيرة. أيضا وبتمنى كل مهندسينا ياخذوا بعين الاعتبار اللايف سايكل اسسمنت، شو بنتج هذا البناء من ثاني اكسيد الكربون في مراحل حياته. هذا البناء الطيني انتاجه لثاني اكسيد الكربون متدني. ايضا الانرجي باي باك بيريود حسبها هذا الباحث سنه 2009 18 سنه، بمعنى الطاقه اللي احنا بذلناها في بناء هذا البيت متى سنستردها؟ امتى رح توفر لنا هاي الطاقه؟ فعناصر الانفايرمنت مهمه جدا، وعناصر بذل الطاقه، يعني مش معقول نحط طاقه هائله جدا في بناء ويكون غير موفر للطاقه. مثل طبعا الابنيه الحكوميه في الاردن، وكلكم بتعرفوا انه بفصل الشتاء بشغلوا التدفئه بيفتحوا الشبابيك. احنا حاولنا في المكتب عده مرات نعمل دراسه لهي الابنيه، حتى الموظفين ما سمحوا لنا نسكر الشبابيك في فصل الشتاء. اذا في ثقافه عامه بتلاقيه متدفي مشوب وفتح الشباك، طب اطفوا التدفئه لا، وطوا التدفئه لا. اذا في عندنا هدر. إعادة استخدام المواد الريسايكل مثل ما شفنا في المحاضرة الأسبق، وأيضا تجنب الطبقة السطحية للطين إلى أسباب لها علاقة بغاز الميثان وغاز ثاني أكسيد الكربون، زائد الكفاءة البناء في العزل الحراري. النقطة اللي قبل الأخيرة مسألة الثيرمال كومفورت في داخل الأبنية القديمة. هاي صور من بيوت قديمة فيها مخازن للغذاء. هاي الصورة اللي على اليسار مخزن للغذاء، مكاور كانوا يسموهم، حطوا الطحين أو القمح من فوق ويطلعوه من تحت. وأيضا خزانة من الأدوبة من القش، هاي كلها كانت موجودة في أبنية أجدادنا. وهاي كونها من مادة ثقيلة أي ثيرمال ماس هي كانت تدفي الأبنية. اليوم الخزاين عندنا خشب مضغوط، تخوت حديد فاضي من جوا، فبالتالي ما في ثيرمال ماس اللي تدفي الأبنية، ولذلك بالليل بنطفي التدفئة بتصير البيت مثل الثلاجة. هاي اللوحة الأخيرة تعطي فرصة لآلاء لأنه الوقت مضغوط. لاحظوا هون بس ملاحظتين سريعات. لاحظوا كفاءة القبب في التبريد. لاحظوا أشعة الشمس والقبة كيف بتحجب مناطق كثيرة من البناء. مناطق السفلية طبعا معزولة حراريا بطبقتين من الطوب، وزي ما حكينا عوازل في الداخل. لاحظوا الشيدنج اريا في أول غرفة نسبة المنطقة الحارة حوالي 20 ل 25% من مساحة السطحية للجدران في الداخل. في الثانية اللي بجنبها تنزل ل 12% فقط. وبالتالي إذا كانت الحرارة السطحية الخارجية 55 حرارة الملامسة، بينما درجة حرارة الهواء برا 40، الحرارة المباشرة إذا بتقيسوها دائما مرتفعة. في الأبنية الأردنية اللي عليها زفتة 70 بتوصل درجة حرارة السطح من فوق، ولذلك بصير البيت فرن بالصيف. إذا لاحظوا كمية، طبعا لاحظوا حركة الهواء سيميوليشن. أنا عملت الأرقام هاي كالكوليشنز باليد، حسبتها يدويا طلعت معي هاي الأرقام. وبالتالي حركة الهواء برضو رسمتها بناء على هاي الأرقام. ففي تيار هوائي طبيعي في داخل البناء، وفي فتحة في السقف زي روزنة بتهوي البناء. فإذا حسبنا درجة حرارة السطح 24 ودرجة جوا 20، وإجينا على آخر كيرف، هذا موجود بالمناسبة بكودة العزل الحراري وكودة الرطوبة في المباني. إذا مشيتوا أفقيا على درجة حرارة السطوح الداخلية اللي هي 24 وطلعنا 20 درجة بيكون في منطقة ارتياح حراري. إذا هذا المبنى مريح حراريا. والآن بدي أعطي دور آلاء. يلا يا آلاء ورجينا شطارتك، يلا. أنا بكفي اللي حكيته. أعطيني اليو اس بي تبعي. بس ما يفصل. ما بس. في أي سؤال سريع بعد إذن مهندس رجاء عبين ما تبلش تشغل اليو اس بي تبعك؟ ما هو على اساس نكسب الوقت بدل ما نضلنا واقفين بدون. طيب اوكي، انت البوس يا سيدي وانت تؤمر. انت رئيس الجلسه. لا فاين فير انف، بس انا بخاف انه تطول. نعم.
ما فينا.
طيب
ما شغل هاخذ من طول الايميل.
اوكي خلاص.
طول الايميل ما قلتش في فيروس ممكن ما قلتش. فعمل احتياطي مستعد.
ما تسمح لي ارد عليه؟ شكرا. طبعا احنا حاولنا نجربها بالاغوار، لا اخفيك، انا كنت مستشار لشركه هابيتات اللي برأسها جيمي كارتر، بنوا ابنيه منخفضه التكاليف في الاغوار، كانوا يرفضوا الناس يستخدموا هذا النمط من الابنيه، كانوا يفضلوا الطوب العادي الاسمنتي. كيف ممكن نستخدمها؟ يعني حسن فتحي استخدمها ببراعه لكن كانت ابنيه مكلفه. كيف ممكن نستخدمها بطريقة تجارية؟ والله أنا بعتقد في إمكانية، ليش لا؟ إذا عمل نموذج، وأنا بتمنى الجامعة، تعرف جامعاتنا التمويل فيها صعب، يعني تطلب مثلا تعمل نموذج زي هذا في الجامعة وتعمل له مونيتورينج. يعني أنا بجامعة مانشستر بالزمانات كسرنا الصورة وعملنا لها مونيتورينج بالتفصيل، واللي بيعرف كتابي عيوب الأبنية نشرته في كتابي عيوب الأبنية عن تشققات في الأبنية. فبالإمكان نعمل نموذج ونراقبه، بإمكان نعمل نموذج ونراقبه بدقة، ومن الخارج نعمل له منظر جمالي مناسب. وأنا بعتقد إنه بيطلع جميل جدا. شوف الأبنية هاي اللي صاروا يبنوها هلا ويدهنوها إدهان بلاستيكي ممتاز، لونها جميل، صرت تشوفها أنت بعد الكسارة بعد ما تنعم بندهن بلون ألوان مختلفة وديورابل وسستينابل وانفايرمنتال جرين. يعني فأنا بدك كم مجموعة من الناس مدعومة من مجموعة أخرى من الناس، وكم من معماري مرتب يطلعوا نماذج مرتبة ويورجوها للناس إنها نماذج هاي ممكن ينسكن فيها بطريقة معاصرة في شميساني وفي جبل عمان وفي عبدون. في كمان سؤال نستفيد من الوقت؟ تفضل. نعم. عفوا. نعم. نعم. والله منيح السؤال، يعني الدكتور بعرف شو توجهه السياسي بس انا بالنسبه لي سوريين ولا اردنيين ولا فلسطينيين كل واحد، فبالتالي هو الازمه وين دكتور الان؟ الازمه وين؟ ما هو الازمه نكبه الشعب السوري، يعني احنا بدنا نحاول سالنا احنا بدنا نحاول نخفف من نكبه الشعب السوري، يعني على الاقل لا دكتور، احنا اخذنا الموقع الزعتري، احنا اخذنا الموقع لاجئين اللي موجودين فيه، الضيوف اللي عندنا اللي موجودين فيه، واخذنا الاورينتيشن تبعه عشان الديزاين. يعني احنا اخترنا هذاك الموقع لغايات انه في امس الحاجه لسكن سريع. هذا السكن سريع، يعني خلال شهر بتكون انت انجزت كل شيء من دون ما تستخدم سيخ حديد، من دون ما تستخدم ايدي عامله محترفه. انت مجرد ما بتخلط الطين وبتشرف عليهم كيف يبنوه وانتهى الموضوع. حتى القبب بناء يدوي، ما في اي تكنولوجيا.
Let's have the speakers here, please. All speakers for all three talks come here in order to answer all of the questions. Since the remaining of their talk is ready. If anybody has any question for Dr. Ramna or Professor Maso, please. Go ahead.
كان حكينا عن انه استخدام الاجهزه العاديه الستاندرد اللي بنسميها على اسبوع يمكن كان عادي مسائل الان 14 يوم شفنا في دروب بالستريت مش مره، يعني ما اعرفش هو بيعرفوا بالموضوع السبب.
شكرا دكتور محمد على السؤال. لاحظوا استطعنا ان نرجع للجراف ونتفرج عليه، وجدنا انه الكونكريت بشكل عام باخذ قوته كامله بعد 28 فوت.
الخرسانه الداخليه بس على اسبوع انت اعطيتنا حوالي 17 ميجا باسكال نزل المفروض انها نفس العينات نزلت على 14 يوم نزلت 13 ميجا باسكال او 14 وين الفكره؟
الملاحظ هو انه عمليه صناعه الخرسانه العاديه ممكن تكون حطت في نفس الظروف اللي حط فيها الخرسانه المدمره. ما كانش اهتمام كبير في عمليه الكيورينج زي ما بنصنع خرسانه سبيشال يعني كونكريت. احنا كان الهدف منها احنا نقارن بنفس الظروف. حطينا احنا المكعبات من الخرسانه المصنعه المدمره والخرسانه العاديه في نفس الظروف، كانت الظروف اذا بيطلع الثنتين عاملين ديكريزنج بعد اسبوع، مش
الخرسانه وصلت 17 شو نزلها؟
بس هي الكيورينج ظروف الكيورينج انه صار عندك ظروف سيفير. هكذا البحث تطرق الى عمليه انه الظروف صعبه جدا ادت الى نسبه ديكريس مش هذا المهم، احنا المهم كان عندنا مش الرسم بشكل عام وملاحظه الدكتور صحيحه 100%، لكن كان عندنا الهدف انه بعد 28 يوم بعد 28 لاحظ ان الخرسانه رجعت اخذت كامل القوه تبعتها، لكن لو قارناها مع الخرسانه المصنعه من الخرسانه المدمره لوجدنا انه في اختلاف يعني مش كبير. الهدف كان انه نثبت للناس انه هاي الخرسانه المدمره ممكن اعاده صناعتها وتصنيعها من جديد بحيث ما يكونش لوز كبير في الستريت. هذا هو كان الهدف.
I think Ala is ready for continuous speech. Okay, you have 5 minutes.
هلا السايت لوكيشن بالبدايه عندنا اخذنا الموجود عندنا في المفرق، اخذنا منطقه المفرق هي منطقه مخيم الزعتري الموجوده عندنا. بالبدايه البوبوليشن كونسيرن الموجوده عندنا نسبه اللاجئين 79554 نسبه عاليه جدا موجوده. بالديموغرافيك بريك داون وجدنا انه نسبه اعمارهم ميل والفيميل من 18 ل 59 سنه نسبه مرتفعه، وهي اللي رح نعتمد عليها بفئه انها تكون الايدي العامله اللي رح تستطيع تبني اليونتس. الستيتمنت اوف بروبلم الموجوده عندنا مشكله بيئيه قبل ما تكون صحيه او اجتماعيه، هي مشكله بيئيه بالحد الاول. توزيع المخيمات الموجوده عندنا نسبه النازحين واللاجئين بازدياد، بنفس الوقت احنا بحاجه ليونتس صحيه توفر لنا تقلل من المشكله الموجوده عندنا باقل التكاليف وبافضل الفرص. قطعه الارض كنا محدودين فيها، بدنا نوجد اكبر عدد من اليونتس داخل هاي القطعه، فكانت الشوارع الرئيسيه عندنا جايه بالطريقه العرضيه اللي هي عرضها 6 متر، لكن بين اليونتس بين بعض هي عندنا ممرات مشاة 3 متر. اليونتس الوحده فيها 16 هاوسز. الهاوس الواحد عباره عن 2 رومز 1 كيتشن 1 باثروم. المساحه للهاوس الواحده 42.5 متر مربع، هي كافيه للمتضررين. بالبدايه ما في شيء اشر فيه. اوكي، عندنا المين رومز هي الغرفه الوسطيه. تمام، هي بالغرفه الوسطيه الموجوده عندنا، وعلى ايدك على اليسار هي الرومز 2 والكيتشن والباث روم الموجودين عندنا، وموزعين بطريقه هاي اليونت هاي الهاوس الوحده في ظهر هالهاوس الثانيه علشان الثيرمال، يعني نستفيد من الثيرمال ماس الموجوده عندنا، وبنفس الوقت للسيفتي للامان اكثر تكون موجوده عندنا. الماتيريال اللي استخدمناها هي عباره عن الطين لعده اسباب. اول شيء هي environmental design environmental friendly material، وثاني شغله فيها انه احنا بنعمل ريديوس للانرجي. ليه؟ لانه لما نستخدم ماده بديله ثانيه احنا رح نضطر ان مصادر نستنفذها او نستخدمها. فالسمنت عندنا بشكل يعني نسبه التلوث الموجوده في العالم 5% من السمنت، فاحنا بنقلل هاي نسبه التلوث لما نستخدم مصادر بديله. بنفس الوقت احنا اخذنا اكثر من عينه منها دخلناها انه نعمل فيها ريسايكل. فخيوط البلاستيكيه الموجوده بكياس اعاده التوزيع للاجئين للقمح، اخذنا الخيوط البلاستيكيه ودخلناها بعينات الطين لسه قيد الدراسه على النتائج الموجوده. وبرضه عندنا عينه للقش وعندنا عينه للبوليسترين. هسه الديتيلز الموجوده عندنا بين الدومز، استخدمنا البلاستر بين الدومز اول إشي بسبب شغلتين، الاولى علشان تحسن لي من الكولينج بريدج الموجوده، وشغله ثانيه بسبب ماده تكون ماده ميلان عندنا علشان المطر. الباس ديزاين تفضل فيها الدكتور ايوب. هاي عندنا الشكل العام للمشروع والإليفيشن الموجوده. الشكل برضو العام للكتله، هاي لتكرارها. شكرا لكم.
Back here, please. We have about 5 minutes for the questions and answers. Where's the microphone?
السؤال الأول دكتور غنام. السؤال الأول تفضل دكتور غنام. نعرف احنا الكونكريت العادية أهم شيء عندنا في الميكس ديزاين اللي هو الووتر سيمنتريشن. في هاي الخرسانة مع تأهيلها وكذا شو أهم شيء يعني؟ شفنا الووتر سيمنتريشن ما لها يعني تأثير كبير يعني. فهذا أول سؤال يعني دكتور. السؤال الثاني في العرض الأخير اليونت الواحدة كم البرايس خاص به؟ كم البرايس لليونت الواحدة لمشروع الإخوة السوريين؟ نعم. اليونت الواحدة كم تقدر تكلفتها؟ شو بدك تشتري؟
إذا بتلاحظ باشمهندس احنا ركزنا في الخرسانة المصنعة، بالعكس الووتر سيمنتريشن كان له أهمية كبيرة جدا، لدرجة إن حكينا في جزء من المي بروح لللوبريكيشن، عملية التشحيم. ليش؟ لأن طبيعة الحبيبات اللي احنا بنكسرها من الخرسانة المدمرة تكون خشنة، بالتالي الاحتكاك كبير. هذا الاحتكاك بيعيق عملية الوركابيلتي اللي أخذتها في الجامعة ودرستها. الوركابيلتي إنه سهولة تشغيل الخط الخرسانية. فجزء من المي بالعكس احنا بنضيفه أكثر من الخرسانة التقليدية، هذا بيؤدي إلى ريدكشن في السترينث تبع الخرسانة، يعني قوة تعامل الخرسانة المصنع من الأجريجيت المكثف والمدمر أكيد بتكون السترينث تبعها أقل من الخرسانة التقليدية لعدة اعتبارات، على رأسها إنه في نسبة مي زيادة وكان الهدف منها عملية اللوبريكيشن. أرجو يكون واضح.
سلام الله. بالنسبة للبيوت هذه اللي تفضلت وجدتونا اياها، هل يعني في امل انه ينبنوا هيك بهذه الطريقه باستخدام الطين والالياف ولا؟
طيب شكرا على الاسئله. فيما يتعلق بالتكلفه طبعا بتشيل الايدي العامله، لانه الايدي العامله سامع مثلا بيقول 200 مليون فهم موجودين اصلا بالموقع. فاذا حسبت المواد مسطح كل وحده 50 متر مربع، التكلفه لن تتجاوز 2000 دينار. هلا شو ممكن انه تتعلم هاي الفكره وبالسؤال السابق، هذا بيعتمد على همه ونشاط نقابه المهندسين انها تدعم هيك مشروع، وانا بعتقد ممكن يكون مشروع تعليمي مهم حتى ما تحتكروا اي جامعه من الجامعات ولا اي مكتب من المكان. انا عندي مكتب استشاري بامكاني انا اعمل هيك مشروع مش مكلف، لكن بصراحه بدنا الطلبه يتعلموا، بدنا مونيتورنج سيستم سستينبل يضل باستمرار موجود، يفحصوا عينات نطور. يعني احنا فحصنا الكومبريشن سترينث ما كان عالي مع البلاستيك، فبدنا يعني ندخل نطور مواد. في حديث ايضا عن تطوير المواد، وهو مشروع متكامل يحتاج انه جهه ما تتبناه كل عناصره وتاخذ عنصر وتعطيه مسؤوليه لشخص معين.
طب ليش ما نبني بروتوتايب يعني بيت واحد على الاقل ونشوف نجرب ما نبني كل المشروع كامل؟
ما انت عارف باشمهندس بدك كمان ناس يسكنوا فيه، يعني بدك تعمل له سيميوليشن حقيقيه. يعني انا جربت اعمل مونيتورنج على بيت الكماليه، بتعرف يعني اخذ اكثر من جائزه كبيره. المشكله انه مش مسموح 24 ساعه 7 ايام بالاسبوع، وبالتالي ما بعطيك انديكيشنز واضحه. بدك بيت واكثر من بيت، حتى عينه واحده لا تكفي، انت عارف يعني على الاقل بدك 3 عينات، 3 عوائل يسكنوا فيه، يعيشوا حياه طبيعيه جدا، وتعمل له مونيتورنج وبالنهايه تعمل كونكلوجنز.
عودة على سؤال الدكتور محمد داوود بالنسبه للستريم تبع الكونكريت اللي حكينا عنه. ملاحظه اللي حكيتها انه حطينا احنا مكعبات خرسانيه مصنعه من الكونكريت العادي ومن الكونكريت اللي جاي من الكونكريت المدمر، حطيناهم في نفس الظروف، في ظروف مختلفه، يعني مره حطيناهم في رطوبه جيده درجه حراره جيده، ومره حطيناهم في سيفير كونديشنز، طلعناهم من الميه حطيناهم برا وخليناهم تحت تاثير ظروف قاسيه، وبالتالي الاطلاع صار ريدكشن في الستريم وعلى اثنين، على الكونكريت العادي وعلى الكونكريت المصنع، اثنين بيصنع. وبالتالي كان الهدف من الموضوع انه نحطهم بنفس الظروف، نحطهم بنفس الظروف. هذا كان الهدف. وبالنسبه للنقطه هذه نتناقشها.
بس عدد العينات كم عينه؟
العينات كانت عباره عن عدد تقليدي، يعني 6 و9 وشيء زي كذا. بالتالي لم نتطرق الى هذا الموضوع. ما قدرناش يعني
I have only one question for Professor Basu. I just want to know how popular is this material being used worldwide?
Thank you. This is still being developed and it is closely guarded by many corporations because it's originally started by military work. As with all the military technology, they get into consumer for some time. So this is started generally I think after the Iraq war. Military was US military started this research. So now it is going into the consumer field. And in India we are very interested because of the use for our roofing sheets. We want to use this material for the low-cost roofing sheets, which can be used for low-cost houses and which can repair itself. You see, the cost of a roofing sheet is an investment which a poor family can afford, and they don't have to keep buying again and again. Heavy rain comes, it damages the sheets, or heavy rain comes, the sheets get damaged. So this is kind of self-repair materials are there to have a longer life. So this is still some of our people are working on this, and we try to develop these kind of materials using some innovative technologies like this. It will have a payoff in the environmental area also, because the cost of making again and again leads to carbon emission. This is a concept to the sustainable and environmental area. But companies are doing what they don't tell. Only when the product comes out, it becomes available. It's like your computer industry. It comes out, you know it, then other people copy it. So it is a game.
Thank you very much. Finally, I thank the speakers, all of them, and thank you very much for your presence, and see you soon, inshallah.